Okay, let's get started. Now that we've covered some very established memory technology, DRAM, and then talked about in-memory computation, and then looked forward to emerging memory technologies that are not that established, but that are hopefully going to be happening. So if you're lucky, we'll see an emerging memory technology next year in the DIM slot. That'd be great, actually. Let's talk about a technology that was emerging like 20, 30 years ago, and that has emerged and that has been extremely successful, and in my opinion that has revolutionized our lives all across. And that's flash memory. And I'm going to give you a short background on flash memory operation. How many of you know how flash memory operates? Oh, okay, that's good. So if I ask you questions, you'll be able to answer? Somewhat. Okay, good. At the very low level? Yeah. Okay. Okay, good. How many of you don't know how flash memory operates? Don't be scared. Okay, okay. Okay, that's good. This will be fun, I think. I mean, like any memory technology, there's now magic in this also. And this is charge-based memory. So basically, I'll give you the high level first. So if you look at NAND flash memory, it's actually very much block-based. Internally, it'll look like DRAM at some point. But the memory array is divided into blocks. And you actually, whenever you need to do a write, you don't need to, basically if you want to write something, you initially erase an entire block. So the block erases are done on a block granularity, and that's to minimize the cost of erases. But you can write at the page granularity, and you can read at the page granularity once you erase the block. Erasing means setting the voltage level to the minimum voltage level possible in the entire block itself. So a block can be pretty large. Basically, it can have 256 pages, for example, each block, and each page is about 8 to 16 kilobytes, for example, in flash memory. So remember, erase at the block level, such that everything becomes 0, and then you can write at the program at the page level. That's called programming, or writing. You write at the page level. And then you can, of course, read at the page granularity as well. Okay, so if you want to read a page, this is what needs to happen. Basically, you need to apply, if you want to read a page in this block, page 0, you need to apply a read reference voltage, which we will talk about what that is, to that particular page. And you need to apply a pass-through voltage to everything else. And this is because of the way flash memory operates, which we will go into. And this is going to be interesting. But this is a little bit different from how we do in DRAM, right? In DRAM, what we did was, if you want to read or activate a page or a row, you applied you applied a high voltage to that word line, and you didn't touch any of the word lines, any other word line. Here, it's different because things are connected in a NAND string. It's called a string, flash string. To optimize for very high capacity, everything is connected in a string. All of these transistors and different pages in a single bit line is in a string, and you need to ensure that whatever you're reading from the string passes through such that you can sense it in the sense amplifiers. And that's how it operates. It's a different technology. That's how it works. Okay, so let's go into a little bit more detail. So this is the block, and these are the pages, as you can see. This now looks like a subarray, as you can see, but it operates a little bit differently. So if you look internally, it looks much like DRAM, except now what you have is these are floating gate transistors. Basically, these are the flash cells that can store data, and whether you have charge or not, encodes data that's stored over here. And this can be very dense, because if you can look at this, it's just one transistor, right? That's it. There's no capacitor. It's just a transistor. And how small you can make that transistor limits your scalability in the end. And this can become very dense. And the rest is similar, basically. You have sense amplifiers at the bottom, you have word lines over here, and you have bit lines over here. The difference is the transistors are on the bit line. Right? If you look at DRAM, if you remember DRAM, the transistors, nothing is on the bit line. You just connect the capacitor through an access transistor to the bit line. Here, the transistors are naturally connected to the bit line, so whenever you're reading one particular cell over here, you need to ensure that these don't interfere with that reading. That's why you need to apply high pass-through voltage to those cells, and you need to apply a read voltage over here. So we'll go through that. So that's a row, very much similar to DRAM, and that's a column, again, very much similar to DRAM, but I already told you the difference. So a flash cell looks like this. It's called a floating gate transistor, at least in planar flash, planar meaning two-dimensional. We'll talk about three-dimensional a little bit also. But in two-dimensional flash, this is the dominant transistor type that has been very successful. It was invented, I think, in, I don't know, late 1970s or so, maybe even earlier. But basically, you have this floating gate that traps charge and stores charge, and you have the drain and source and the gate, as you can see over here. And you store the threshold value, threshold voltage of this cell that you program it to determines the value that you store over here. So you can, for example, program this. This is usually programmed with what is called incremental step pulse programming. If you really are interested, you can read some of the papers that I'm going to reference. But incrementally, you increase the voltage over step by step. Basically, you have these small voltage steps, and you incrementally pump voltage into it and increase the voltage to a level that you want it to be at, such that that level is encoded as whatever you want the cell to reflect in terms of data, right? And we will see that also. So let's assume that the threshold voltage is 2.5 volts, right? And when you program threshold voltage, after you program it, you apply some other reference voltage, and the cell reacts in some way, depending on what the voltage that it's programmed to is over here. So it can actually store the voltage forever. It's non-volatile, at least forever, meaning theoretically forever, of course, right? But in practice, you have a lot of other effects. Okay, so this is threshold voltage. Basically, this is on the x-axis, you have this normalized threshold voltage, and we'll see a lot of these graphs over here. Right now, this is a flash cell with very few electrons programmed to it, low voltage. You can encode that as a 1. And this is a flash cell with lots of electrons programmed in the floating gate. Basically, this is high voltage, and you can program, you can encode this as a 0, right? You can assign any kind of logical encoding to these two different states. And then you have a boundary between these that tells you what is the difference between a 0 or 1, basically a reference boundary over here, and we will see that also. So basically, let's take a look at two cells. One is programmed at 2 volts at threshold voltage, and the other has a threshold voltage of 3 volts. And let's assume your boundary is 2.5 volts over here. What you do is, if you want to distinguish between what the cell is containing right now, you apply this read reference voltage that you know is 2.5 volts, because that's how you program the cells. You apply this read reference voltage to it. Now the cell turns on, meaning basically passes the value if the read reference voltage is greater than the threshold voltage. In this case, it's like that. You get a 1 over here. Now the cell is inhibited if the read reference voltage that's applied to the gate is lower than the threshold voltage. It doesn't turn on. As a result, it inhibits what's coming from the bit line. Remember, there's a string of transistors over here. As a result, you get a 0 over here. So that's how you distinguish between these two cells. You apply a read reference voltage that's known, and one of them reacts with a 1, and the other one reacts with a 0, which makes sense, right? Okay, that's the flash read. Okay, I think I've already given this. Okay, so pass-through, so this is how you can distinguish the value. But if you don't want to read a row, what you do is kind of obvious. Pass-through means you apply a very high voltage that's higher than any value that any cell is programmed to, and then you make sure that this cell passes through what's coming. The cell turns on, and it passes through what's coming over here. That's the idea over here. That's how you ensure that some rows pass through the values that are coming through the bit lines. You apply a very high voltage. That's called the pass-through voltage. Make sense? Okay. So let's take a look at the read from a cell array with an example. Let's assume that we programmed the cell array to these values somehow earlier using incremental step pulse programming. But there are other programming methods people have developed, but ISPP tends to be the most common one today. Let's assume that we want to read page 2 over here. If you want to read the contents of page 2, we want to apply the read reference voltage to the word line of this page, and we want to apply the pass-through voltage to all of the other word lines over here. Essentially, this is what we do. And when we do that, these two transistors are inhibited because their threshold voltages are higher than the read reference voltage, so they don't pass through what they have. So you get a 0 at the end, whereas here they pass through what they have, so you get a 1. And these don't interfere because they're always turned off if you will, right? Because the pass-through voltage is, at least the voltage that you apply to the gate is always higher than the values that you see on these pages that you're not reading. As a result, in the sense amplifiers, you get 0, 0, 1, 1, which is really what you want by reading that page. Of course, there's a sense amplification process over here also, which we're not going to talk about. Okay, there's an aside that I wanted to put over here. I wish I had made these figures a bit larger, but the difference between NAND and NOR, you may actually see NAND and NOR flash memory. NAND flash memory is much more common today because of its very high density. NOR flash memory is not that common today, although its latencies are relatively low, its density is not very high, and it may not be as scalable. But we're not going to go into the NOR memory as much. At some point in the lifetime of overall history of flash memory, there was a big debate which one is going to be more successful, which one is going to be better. And it turns out that NAND flash memory won because of its density advantage. And as you can see, the density advantages, the bit line looks like this over here. Basically, this is the bit string that you have, and all of these transistors are connected to the bit line in a NAND fashion, which is what we actually looked at over here, which was NAND. Whereas here, it's like a NOR fashion, basically. You can see that the bit line is like this, and the bit line turns on if any of these transistors actually turn on. But as you can see, this actually is not very dense. So you have a lot of these additional lines, as opposed to having a single string where you can really nicely put things on. Here, you don't have that single string. But the word reading is relatively fast over here because you don't go through the entire string. So the capacitance is much lower over here. So we're not going to talk a lot about NOR memory because it's not as high capacity, but it's interesting in the sense that it's a different type of flash memory. It uses the same type of transistor. They're organized a little bit differently in a NOR manner as opposed to a NAND manner across the entire bit line. Okay, makes sense? But this is also fast. The advantage is this is fast. Faster than NAND. Okay, let's go back to the threshold voltage. Basically, this is what we said. You want to program the cells. You have a read reference voltage that delineates a 1 from a 0. And if you want to program a cell to the 1, you program it to this level. If you want to program it to the 0, you program it to this level. Now, naturally, there's a lot of variation in the programming. Programming cannot be extremely precise. So whenever you do the programming, your threshold voltage will not be exact. It turns out there's variation. So usually what happens is you have a distribution across the flash cells that you programmed. If you program them to 1, some of them have threshold voltages that are over here. Some of them have threshold voltages that are over here. If you program them to 0, some of them have threshold voltages that are over here. They're really close to this 1. And some of them have threshold voltages that are around here. And this happens because of program variation, which is a factor of process variation, how precise your programming equipment is, and many, many other factors. The factors in terms of cell as well. And the papers that I'm going to reference actually look a lot into those issues. But yeah, this exists, and you have to deal with it. I mean, this is also true for DRAM cells, actually. If you remember, DRAM cells store different amounts of charge, except we never showed them in this way. We show them in this way because we actually are a little bit more precise in terms of how much voltage we inject. And we can actually read the reference voltages that we program cells into in flash memory. We have a lot more control because of the machinery there. Okay, so basically you will see these threshold voltage distributions. This is called the threshold voltage distribution. It's a normalized threshold voltage, and it's probability density function, as you can see. So this is more highly probable. This is more highly probable. And this is the threshold voltage distribution for state 1 and for state 0. Okay, and a lot of problems will appear because these threshold voltage distributions are not that nice as I depict over here. They actually overlap with each other, especially with a lot of factors that happen. And that's exactly why it's hard to make these memories work. But we're going to develop a lot of techniques to make them work. So okay, basically you select your read reference voltage such that it's actually hopefully nice. It basically delineates this distribution from this other distribution such that you get no errors. Right? If these distributions were overlapping, you would get errors. And we will see that. Okay, so this is called single level cell, meaning a single cell denotes a single bit. But if you want to go to multi-level cell, as we've discussed with PCM, it's relatively similar. You chop up the threshold voltage range into 4 in this case. And now you have different states. You have an erase state. It's usually called an erase state because this state is actually not programmed, right? You erase the block, and if you don't want to change the value from that, you don't touch it. You don't program that cell. Actually, it usually has negative voltage because you don't touch it. You raise it to 0, and over time it drifts to negative. As a result, we're not going to show it. We're not going to be able to even measure it in a lot of distributions in real life. Okay, but this is, you need to program this P1 state to 1, 0, and P2. In this case, I encode as 0, 0 for the reasons that we've discussed in the past. But again, you can put any encoding here, and this P3 set. So now you've seen that actually the threshold voltage distributions became much narrower. And maybe you don't have enough control to actually make these read reference voltages nice as I showed you. Okay, so the upside is you get higher capacity, clearly, with the same threshold voltage range. You didn't change anything in the structure, but you chopped up the threshold voltage range into 4. Higher capacity, you doubled the capacity. But now you need to use 3 different threshold voltages to identify a cell's value. And the other downside is your reliability may have reduced because your distribution may not be as nice. The distribution may actually span partly these threshold voltages. So as I said, the erased state is actually erased. You don't program it. So we're not going to see a lot of the erased state in the measurements that we will see because it usually has negative voltage. Okay, so we're going to look at things like this. There are 3 states to encode 4 values. There's also the erased state, but we're not going to measure it. So these 3 states look like this. But there are issues. Like one issue we're going to talk about is over time, charge gets lost. That's the fundamental issue with charge memory. So when charge gets lost, what happens is these threshold voltage distributions shift like this. So they've just shifted, as you can see, from here. Maybe it was nice to begin with, but over time, some of the cells lose charge and they shift. Now what happens is, if you were reading using this read reference voltage, these cells were correctly read in the past, but now they're going to be incorrectly read as 0, 0. You were thinking they were 0, 1, and they were correct, but your read reference voltage is wrong. I don't want to say wrong now. The cells actually shifted to a value that's below the read reference voltage. As a result, you get bit errors when you're reading this cell. And that's true for this side also. All of these cells that are in this distribution that have shifted to the left of this threshold voltage, this read reference voltage, are actually going to be read incorrectly. So that's a problem. So what you can do is basically if you have a fixed read reference voltage, that's what happens. But if you're able to adapt your read reference voltage to what's happening in the device, you can say, oh, okay, some of these cells actually store data for, let's say, 5 days. And because they've stored data for 5 days, my read reference voltage should not be this, but it should really be this. If you can find that out, then that sounds good, because this is the place where you really minimize the raw bit errors, right? You really want to be crossing the point. You really want to be at the point where the distributions cross if you want to minimize the raw bit errors. And that's exactly one of the mechanisms that existing flash controllers use. This is called the optimal read reference voltage. They basically try to find the optimal read reference voltage to minimize these raw bit errors, because these raw bit errors are a lot. I'll show you real distributions from very small devices in a little bit, and you'll see that they actually overlap very heavily. Okay, makes sense, right? So how do these real controllers do this? Basically, they have a mechanism called read-retry. They are able to actually change the read reference voltage and check the value, check the number of errors. So what is usually done, one algorithm is, for example, they read with read reference voltage, and then they get the values. The values go through error correction. If the error correction doesn't pass, they change the read reference voltage and read again. That's one algorithm. Of course, existing controllers are even more sophisticated today. They don't even try, because that's not a good algorithm in the sense that increases your read latency, right? Especially if you want to do it many times over and over, because these steps, the voltage steps, are relatively small. If you want to get to a point where you don't have errors, hopefully, if it's possible, you want to find the read reference voltage that gives you a read that's correctable by ECC, right? But that may take time. That may take like 10 steps, meaning that 10 times you do the read of the flash. That doesn't sound good, right? It's already a slow device. If you're doing the read 10 times to get the right value, that's 10x more latency. So what existing controllers will do is use techniques that I'm going to describe a little bit. They actually try to predict what the threshold voltage would be over time. And they don't try to, they try to minimize these retries as I described them. They try to predict, okay, maybe 5 days later the threshold voltage will be this, so they try to adapt the read reference voltage. So there are a lot of models that these controllers actually build, and they're building them online, during online operation today, to basically characterize the distribution and basically characterize, have a model inside that basically predicts, okay, the distribution will be like this, given that the data has stayed here for n days, given that neighboring page have been programmed, maybe with these values, and as a result, I'm going to pick a read reference voltage that's here. And we're going to talk about some of those models, but there's a lot of very, very interesting research that has gone into it to minimize these raw bit errors, because these raw bit errors are actually a lot. Okay, so how do you actually program these cells? Actually, if you have a 2-bit multi-level cell NAND flash memory, you normally program it using like two-shot programming, what we call it right now, and that increases your latency. Basically, what you do is you normally program the LSB, or least significant bit first. Essentially, so this is the first step, or two-step programming. Sometimes actually there are two types of programming mechanisms. One is called one-shot programming, and the other is two-step programming. A lot of flash memories use this two-step programming because it's more precise right now, because you program one bit first and then the other bit next. But actually, if you have a very large cell, sometimes it's okay to use one-shot programming. And actually, with 2D NAND, cells have become very small, the planar NAND. As a result, people move to this two-step programming a lot. But this, of course, increases your latency. But when actually people were able to figure out how to do 3D NAND, they increase the cell size. So they're back to one-shot programming. Meaning that they can control the cell more precisely. As a result, they can actually program 2 bits at the same time. But that's going to change again, I think, as things scale. They're going to go back to two-step programming like this. But basically, what is two-step programming? You program the LSB, least significant bit first. So in this case, least significant bit is, I guess, 1 or 0. So basically, erase state, you don't do anything. If your least significant bit is 0, you go to this temporary state. Temporary state, you don't know. It could be any of these, right? If the least significant bit is 1, you don't do anything. If least significant bit is 0, you go to this temporary state. And then you program the most significant bit. Well, I guess if your most significant bit is 1, you move from the erase state to this P1 state by adding some more voltage. And if your most significant bit is 0, you go from this temp state to this P2 state by adding some more voltage. And then if most significant bit is 1, in this case I encoded things a little bit differently. The most significant bit is on the right, least significant bit is on the left. So this is a big endian, as you can see, which I don't like, but that's how it happened to be. But basically, you program the second bit next over here. As a result, it's two-step, and this takes time. This takes time, and then this takes time. But it's more precise because you're doing it in 2 steps. Okay. Okay, so if you look at multi-level cell architecture, it actually looks like this. I'm not going to go through this in detail, but basically, you have these LSB even page sets. You can see them over here. And then you actually have LSB odd page sets. These are least significant bit. You have this separation between odd and even pages. And then you have most significant bits over here, even and odd. But you can read the papers for more detail. It's nothing different from what I just described. But the difference over here is, as you can see, whenever you're programming, the interesting thing over here is whenever you're programming, you apply very high voltage. So this is about 20 volts in this example. That's a lot. And you also need to inhibit everybody else. That actually is about 10 volts. So programming these things actually take a long time. That's why the write latencies are long and the energy is very high also. So ideally you want to program minimally. Okay, do I have anything over here? Okay, the other thing I have over here is nothing. Okay, you can see the MSB and LSB over here also. That's fine. But basically, if you see these figures, that you should think about corresponding these to these states over here. One thing that I will talk about over here is the order in which you program things matter. So you usually, as I said, this is LSB odd page sets, MSB even page sets. So the order in which you program things matter because whenever you program, you cause interference to the adjacent word lines because of these voltages that you apply. And the way people usually do programming of pages after they erase a block, the way the pages are programmed is they want to minimize that interference. And there are algorithms that are developed to minimize that interference. I'll point you to a paper that talks about that. It's interesting, but it's basically you want to minimize the interference such that you don't destroy the values in the pages that are next to you. That's the idea. So that's called write disturb essentially, or program interference. Okay. So controllers need to be aware of that also. So let's talk about planar versus 3D NAND flash memory. For a long time, planar memory was very, very successful. It was hitting the scaling limits, just like DRAM is hitting the scaling limits right now maybe, because it was two-dimensional. Basically, people scaled the cell by reducing the cell size, reducing the distance between the cells, and as a result, they were able to get high capacity. And what's the difference? This is two-dimensional, as you can see. Three-dimensional NAND flash memory, you stack these cells, and I'm going to show you an example of this. Basically, you can increase the number of layers. So this turned out to have scaling issues. Scaling actually hurt reliability a lot, and a lot of methods have been developed to improve the reliability, to make this work, basically. And we're going to talk about a lot of those methods. 3D NAND flash memory, recently, this is actually a revolution within the flash memory. People invented how you could stack the floating gate transistors in a single bit line vertically. And now, because they were able to do that, they actually broke the boundaries of this 2D planar thing, if you will. And they were able to actually stack things vertically. Now they have another level of freedom, right? You could actually put things in a vertical way. And as a result, they were able to increase the size of the cell. Here, the size of the cell was 1x nanometers or 1y nanometers, 10 to 15 nanometers. Here, now the size of the cell is 30 to 50 nanometers. So actually, they increased the size of the cell, which is good for reliability. And they were able to get high capacity by actually stacking many, many layers. So there are existing chips that are out there that have 96 or so layers in 3D. The issue is, of course, this is not well studied, and we're going to talk about some works that are studying it. So this is actually a very open and very interesting area in terms of reliability as well as other optimizations in 3D NAND flash memory. Okay, so this is an example of 3D NAND. Basically, it's kind of obvious, but you have these bit lines that are vertical, and the layers are actually horizontal, and layers are actually word lines over here. And we're going to look at inside you have these transistors over here. And most of these are charge trap transistors. So this is the flash cell right now. And this is a charge trap transistor. There's multiple technologies. You could actually have floating gates over there also, but charge trap tends to be easier to manufacture right now, although in future we will see what happens. Basically, the way this works is relatively similar to what I just described at the abstract level. But internally, the way it's implemented looks like this. You have a substrate over here. You have a charge trap. And you trap the charge inside this charge trap transistor. And you have the control gate and the gate oxide and the tunnel oxide. OK, I don't want to go into the detail. You can read the paper again. But you can see this nice picture. This is basically, it's nothing different from any memory that we examined, except it's three-dimensional, right? This is the three-dimensional bit line. It goes across, and this is the word line that cuts the bit line. And your blocks look like this now. Your blocks are essentially three-dimensional, if you will. And this is the other block, and this is the other block, dot, 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 right? And you have the sense amplifiers at the bottom. Make sense? OK. Add another layer, of course, that's a sense amplifier layer. OK, so if you're interested, actually, there's a lot more background. And we recently written a survey, an invited survey paper that talks about flash memory, as well as many, many other things that are employed in flash memory. And that was published in Proceedings of the IEEE. I would recommend that you take a look at it. This is really, we put like more than a year of effort into writing this paper, and more than 8 years of research that we have done, and also we have observed based on what other people have done. So this is really the state-of-the-art summary. I'm very proud of it. And it's about 40 pages or so, I think. But of course, after we wrote it, we know that it was obsolete at the moment. And then we wrote the more up-to-date version, which is also obsolete at the moment. But at least it's the most up-to-date version that's out there right now. So this was actually The more recent version that's on archive.org, it's also in this book that's called Inside Solid State Drives. That is actually a lot of other stuff related to solid state drives. If you're interested in that, you can look at the book as well. But it's not my book, other stuff. This chapter is ours. So this is actually more up to date because it talks about 3D NAND a little bit more, but it doesn't really have the most state-of-the-art things in 3D NAND. So the more up-to-date version is hopefully coming in 2019 or maybe 20, depending on how much time I have. Okay. But this actually has a very accessible view of how flash memory operates. It talks about other stuff like garbage collection, which we're not really going to talk as much about today. Okay, maybe I'll talk about it. But maybe I'll talk about garbage collection a little bit. So garbage collection is, you have these pages in flash. So if you want to write to a location, change the value of a page, it's not easy, right? As we've seen. What do you do? Because let's assume that you have read this page and that you modified the contents of that page. Now you need to reprogram it. Reprogramming it is not easy because you cannot just write to that page, because when you want to actually reprogram, you only can increase the voltages. If you want to decrease the voltage, you need to erase it. But there is no mechanism to erase a single page. Erases are done only at the block granularity. And this is a trade-off that was made for cost reasons, because erases are actually extremely expensive. As a result, flash manufacturers said, we're going to do erase at the block level. And as you saw, blocks are 256 pages, right? And you do erase at the block level, but you want to modify only that page. Now you have a problem. You read the page. What do you do? Well, what you do is actually have blocks that are writable at that moment. So you have a set of blocks. Some of them are erased. Some of them are currently being written. And some of them are valid, meaning you already have valid data inside them. And the flash translation layer needs to keep track of them. If you want to read a page and write to it, what you do is you read the page, you modify the value, and write it to some other block that you're currently writing to. Which means that you actually remap the page, right? You remap the page from this location to this location. So flash translation layer, one of the big jobs of the flash translation layer is to keep track of what block exists where, because it does a lot of these remapping. You have a logical block address that gets remapped to physical locations, because whenever you modify, you actually cannot directly modify, you need to remap it. That's the idea. Now, okay, you remap this page from this location, from this block, to this other block. Actually, let's give an example over here, if we can. We have block 0, let's say block 1, block 2. Let's say this is completely erased somehow. And this is the block that you're writing to. So open for writing, I'll call it. Meaning some of them are erased and some of them are being written to, because you've just erased it and you're directing your writes over here. And this is a block that is basically, let's assume that it has, it's not erased, it's not open for writing, it's populated. So these are 3 different types of blocks. This block you cannot write to, because writing requires erasing. This block you can write to some pages. And this block, yes, you can write to, but you're waiting such that you can utilize this part first, because this is open for writing also. So this is open for writing. This will be open for writing in the future after you're done populating this. So basically, flash controllers need to maintain a logical block address to a physical block address mapping table. Your logical block address, let's say, I don't know, is 0. Initially, it's mapped to here. But when you want to write to it, you read the block with the reading mechanism that we discussed. You modify 1 bit. Doesn't matter how many bits you modify. You modified 1 bit. You need to write the entire, this page. So this is actually at the page level, right? Because you're doing operations reads and writes at the page level. You basically write to this page 0 and block 0. which means that you read the data, you modify one bit, and you write the page to the next available physical page in the open block that's open for writing, which means that you need to change this pointer in the flash translation layer from here to here. But which also means that the flash translation layer needs to be aware of everything. Now what happened to this? That's obsolete. That's stale value. So flash translation actually keeps another table that says these are my invalid pages. I mean, this could be organized in different ways, of course. And this could be one linked list. So one of the invalid pages is block 0, page 0. I've written it somewhere else. So that's invalid. I cannot do much to it. I cannot erase it. There's some value over there. So it's basically invalid. It's waste. Okay, so let's assume that you've done some of these to some of the other pages over here. And remember, this is 256 pages, let's say. And let's assume that you've written 200 of them somewhere else, because you're writing to those blocks. You've changed their mappings. Now you have only 56 valid pages here, right? Meaning that you're really wasting most of your block right now. So actually this is, so what should the controller do right now? So sometimes, this depends on the algorithm of the controller, but sometimes what the controller says is, heck, I don't want to waste a lot of this, so I'm going to move those 66 pages to a block that I erased. In the background, I'm erasing stuff because I'm smart. Make sense? So that's one way of doing it. So this is kind of an example of garbage collection, because these invalid pages are actually garbage. Meaning you don't care about the data in them, they're just wasting space. So you want to maximize your space utilization inside the drive. As a result, you need to collect that garbage once in a while. And this is an example of garbage collection. So how do you set the threshold? Maybe you wait until there are no valid pages here, right? Then that's really garbage. The entire thing is garbage, then you can erase it. But you can be proactive also. You can say, oh, I'm wasting most of my space in this block, so I'm going to declare this as mostly garbage, and I'm going to move the useful stuff to some other block, and then I'm going to erase it such that somebody else can use it. So controllers are doing this in the background all the time to ensure that they have enough space over here. And this is happening because the read and write granularity is at the page level, and erase granularity, well, I shouldn't say write granularity. Okay, read granularity is at the page level, and the erase and program granularity is at the block level. And the block level is huge. And that is there because of technology constraints. So of course, to be able to do that, what the controllers usually have is, usually the space in flash drives are over-provisioned, meaning that they actually have more blocks than advertised to the customer, so that they can actually handle this sort of moves more efficiently. Of course, over-provisioning is not good in general. Ideally, you don't want any over-provisioning because that costs, right? You would like to minimize the over-provisioning, but over-provisioning happens naturally because you want to handle these cases. Okay? Then the key question, there's actually really interesting questions over here. Like now you have actually another level of freedom. You have these different pages, and maybe you know their characteristics. What should you collocate in a block? Ideally, you want to be smart about this also. If things are going to be written a lot, maybe you collocate them in a single block. If things are not going to be written a lot, maybe you want to collocate them in a single block also. But you don't want to mix them. There are some pages that are very hot in terms of writes, and there are some pages that are not very hot in terms of writes. If you mix them, you run into the situation that I just discussed over here. Some of them will be garbage, some of them will not be garbage, right? But if all of the pages in your block are very hot in terms of writes, you keep writing to them, that's good. Put them all together such that that block quickly becomes garbage and quickly becomes non-garbage afterwards. And if you have a collection of pages that you know are not going to be written a lot, they're read-only, maybe you keep them in a single block. That way, that block is not going to be touched much for a long time. That's one trade-off. So that sounds good. Of course, it's not that simple because of other issues with the device, right? The device has another issue which is called wear out. So if you keep writing to only a single block, that may be good for this garbage collection purposes, but that's actually terrible for wear out purposes because you keep wearing out the same block all the time, right? So you want to balance that. You need to actually do the wear leveling across the blocks or across the pages actually to ensure that you want to distribute, you want to have a, because, okay, what is this is the endurance problem that we discussed. A block, for example, you can only do 3,000 writes to a given block. 3,000 program and erases or page. Now, if some of the pages have over here 3,000, if some of them have 0 over here, that may not be good, right? Because you're not utilizing your entire drive. Some of them becomes unusable quickly, and some others become unusable, right? Maybe it's better to level this wear or wear out across the blocks somehow, such that you level the number of writes across the blocks. The question is, how do you do that while also trying to minimize the garbage that you have? That's why the design of the control is actually a very complex design, because these things actually go against each other. And also there are other issues. Like if you actually say, okay, I'm going to collocate these blocks that are read very heavily in the same block, there are other error mechanisms that you need to watch out for, because there are read disturb mechanisms that we're going to talk about. If you're reading a lot, a particular page, you're disturbing other pages. So your reliability for that block may go down, and you may need to have more ECC or mechanisms for that. So what data to place where becomes actually very, very interesting, given all of these different constraints. And there are many, many different constraints, and we will see some more of them soon. Okay, so I said I don't want to talk about garbage collection, but you know what garbage collection is right now. Okay, any questions while I do this? Okay, so let's talk more about flash memory reliability, because in addition to all of these latency and performance issues, reliability is very, very important. And I'm going to focus more on reliability right now, because that's something that's really required to make the memory work. And I think I said at some point that this memory doesn't work off the bat. You really need a controller that's intelligent to make it work. By the way, I talk about erases, but these erases take a huge amount of time. So they take 10 to 100 times longer than a read. So scheduling is another issue that we're not going to talk about, for example. How do you schedule these requests? Because you have read requests, you have erase requests, you have refresh requests, as we will talk about. How do you schedule all of these requests to flash memory becomes interesting. Ideally, you would like these erases to happen in the background. That's what these controllers try to do. They try to make sure that while things are idle, if they happen to be idle, they erase as many blocks as possible, such that those are available for writing later on, but that's not always possible, of course. They try to minimize interference. So these are some of the issues that you should keep in mind, but we're not going to talk about all of them at the same time. But let's talk about errors, because this is actually a fascinating area. And you know this picture before. Flash memory is charge-based memory, so it's prone to a lot of errors because of charge. So I'll cover a bunch of hopefully really interesting works. This is an executive summary of it. Basically, NAND flash memory reliability and endurance is a key challenge for satisfying future store systems requirements. I'm going to talk about that a little bit. And then I'll talk about some of the works that we have done and that are being employed in the field that are based on two goals. One is we want to actually build reliable error models for NAND flash memory via experimental characterization, similar to what we've done for DRAM, for example. But we can be much more precise over here because we have the luxury of measuring the voltage of every single cell. It's not possible to do that in DRAM. And we'd like to develop efficient techniques to improve reliability and endurance. So basically, this is going to be a flash summary of recent results that talk about experimental error and threshold voltage characterization, retention of error management, and a bunch of other stuff. We'll see that. Okay, and actually more, but it doesn't fit over here. So let me give you some more high level. Basically, this is a picture from 2011 from Hynix, actually. And this shows what flash memory has gone through in terms of scaling. So it's actually, it's like scaled perfectly almost until somewhere around here. You can read the numbers over here, but this is MLC flash memory. You can get 64 gigabits, and basically you get very good scaling. That's what I should say over here. And as a result, it's actually widened its range of applications everywhere, because you could put a lot of bits into a very small space, much more dense than DRAM, less dense than hard disks, but hard disks are actually very cumbersome, right? They're huge, and they're totally different technology. As a result, they don't have the good characteristics of flash memory. Okay, the key question at that time was actually how do we scale into the future? And this actually is still a question, but it's delayed a little bit more because of 3D NAND. So this is one example over here. This is again from Flash Memory Summit in 2012. If you look over here, this is years, and this is the program erase cycles. How many program erase cycles can a page endure before it gets dead, before you cannot read from it or write to it? And if you look over here, this is single level cell. It looks good, 100,000 or so. This is multi-level cell. It's about 3,000. And this is triple level cell. You store 3 bits per cell. And that's very low. It's getting close to 100 over here. And actually, some more aggressive ones I know are 100. So the provided program erase cycles are a few thousand, let's say. Pick this one. But if you look into storage requirements, the program erase cycles that are really required, these are standards actually, is by STEC, that's a storage technology corporation that a lot of companies get together and they say, okay, we want to be able to write the full capacity of the drive 10 times per day for 5 years. If you want to do that, you really need more than 50,000 program erase cycles with a decent capacity. So there's a mismatch over here. The device provides a few thousand, you really want more than 50,000 if this is your application level requirement. So how do we bridge the gap? So one way of bridging the gap is of course over provisioning, right? The device advertised itself to be 1 terabytes. Internally it's 4 terabytes. Now it can actually manage itself, but that's not a good solution, right? That's an expensive solution. Remember, expensive solutions are possible, but that's not the goal. An engineer is someone who does for a dime what any fool can do for $1. Okay, so basically, how do we bridge the gap? We're going to talk about bridging the gap. So one way of bridging the gap is potentially using ECC, but I'll actually show that it's not a very good idea, perhaps. So this is another view of this. This is again from 2011, but the trends are actually very clear at that time. So this is single level cell, this is 5x nanometer multi-level cell, 3x nanometer multi-level cell, 2x nanometer multi-level cell. You see that endurance is decreasing. And it's 3-bit, so endurance is about 1,000 cycles. So endurance decreases with scaling as well as multi-level cell as expected. So if you want to, you can actually add error correction capability. And if you want to guarantee storage class reliability, which is uncorruptible bit error rate is less than 10 to the minus 15, you actually need to add a lot of ECC. So the bit error rate is a little bit different from endurance. Bit error rate is how many bits are erroneous. 10 to the minus 15 is something that you would like to achieve. If you would like to achieve that, you actually want a lot of ECC. So this is error correction capability is 4 bits per 1 kilobytes of data. Here you need 24 bits per 1 kilobytes of data. In Flash, error correction is done in large blocks. We're not going to go into that in detail. Some of the papers talk about that. But basically, you need more bits, more redundant bits, which actually takes away from your space also, right? So this graph is very telling because you're actually getting less endurance, but you're putting more ECC inside the chip to get the high error rate. So how do you actually, basically ECC is, the ECC that you require is increasing exponentially to reach less endurance, but keep your error rate at least at 10 to the minus 15. So this doesn't sound good. So this was a clear scaling problem, and that's one of the reasons why we wanted to look into this from the research perspective. And when we first started looking into this, actually, we were behind industry, meaning that industry knew a lot more than us. Now I think industry knows in some areas more than us, but we could actually affect the industry because we are able to invent, and they take some of the ideas. So sometimes it's good to actually go into research even though you know that you're behind, because you can leap forward much faster. Okay, so basically the problem is the NAND flash memory is increasingly noisy. you can think of a single bit, even a single cell, as a channel. You write into the cell, and something happens while you're writing and while the cell is sitting there, and then you read something out of that channel, and what you read may not correspond to what you write. So you can think of this as a communication channel, right? You have a communication channel over here that happens to be the cell. You transmit on this end, and you read on this end, and things happen in between, and you can model what those things happen. But a lot of things happen actually in between. So let's talk about that. It's a noisy communication channel. That's why I think actually communications people look a lot into memories as well. I think this is a very good approach to examine memories as communication channels. Okay, so basically, if you look at flash, you have some noisiness, and you get some row bit error rate that's usually high, and you want to do something to it such that your uncorrectable bit error rate is less than some requirement. So you clearly need to apply some error correction mechanisms somehow. You need to be intelligent about them. And maybe you need to apply something else such that you reduce the row bit error rate that you get over here. I'm going to call that signal processing, because a lot of these things will look like signals. Okay, basically you want to minimize the raw bit error rate that we get out of these devices, and we want to actually do better error correction or more intelligent error correction such that we satisfy the requirements. So how do you actually do this? First, you need to understand. As I said earlier, for DRAM, you want to be able to understand. You want to build the reliable error models for NAND flash memory. And you want to design efficient reliability mechanisms based on the models. Let's take a look at what happens to a flash cell over its lifetime. So first of all, you write into it. What we wanted to do was to experiment to characterize and model dominant errors. So what are those dominant errors? And this is the first paper that I'm going to describe that was published in 2012. So you write to the cell. What does that mean? You need to erase a block at some point. You need to program the page. And you get errors in both. Whenever you're erasing a block, erase is not a complete clean erase, because you get errors. There is no erase that's error-free in flash. That's the beautiful technology, unfortunately. And then you program a page, you get errors. You actually inject errors to others. So we're going to talk about some of the errors that we characterized. And then while the cell is sitting there, you're not even touching the cell anymore. You programmed it, you erased the block, you programmed the page, fine. Now some neighbor page gets programmed, and whatever you have in the cell gets disturbed because of cell-to-cell interference. And you need to understand that. And there are ways of understanding it and ways of building mechanisms to overcome it. And we're going to talk about that. Okay, that happens. Even if nothing else is happening around the cell, neighbor page, by the way, is any page around in the same block. So you actually have 256 minus 1 pages that can affect you while you're sitting there. And even if nothing affects you, you're subject to retention errors, because the data over there is sitting and you may not read it for a really long time, and charge leaks. As a result, you have a retention problem, and you need to deal with that somehow also. So we're going to look at some of these errors, and as I said, a lot of these are, actually all of these are described in that paper that I mentioned that I'm proud of. Okay, so let's talk about the goals again. We want to understand these error mechanisms and develop reliable models that are predictive for the flash memory errors, and develop efficient error management techniques to mitigate errors and improve flash reliability and endurance. As I said, you want to improve reliability, improve endurance, and also improve the row bit error rate. So basically, we're going to do a lot of experimental analyses of real MLC NAND flash memory that will drive the understanding in the models. And hopefully understanding models and the creativity associated with architecture will drive the new techniques. And here's another example from that paper that I mentioned. These are the different types of errors. Program erase cycling, that's wear out. Program cell-to-cell interference, data retention, read disturb. This is in planar flash. There's also some more in 3D flash. And these are some mitigation mechanisms that we're going to talk about. Maybe not all of them, but I already talked about hot data management, for example. That's employed in flash drives, but maybe it's not the best way. It's not employed in the best ways. Okay, and I'll point you to those papers. So let's talk about the experimental characterization methodology a little bit. So we're going to characterize these errors, meaning that you actually really need to have an infrastructure to be able to do that. And this was the infrastructure that we had. This is an initial incarnation of the infrastructure. It's relatively similar to the DRAM infrastructure, and we have a NAND flash controller, and we have a flash translation layer, in this case, inside the FPGA. And let's talk about the first error types that we're going to examine. There are 4 different error types. 3 of them are caused by common flash operations, and we're going to initially characterize these: read errors, erase errors, and program interference errors. And one of them is caused by flash cell losing charge over time, and that's the retention errors. And of course, whether an error happens depends on the required retention time, when you're going to read the data. For example, if you're going to store your pictures in a USB drive and you're going to read them 6 years later, that's a lot of retention time. You may want to read them earlier, because those drives are actually some of the worst flash memories. And they are subject to all of those errors, and they don't have many of the error mitigation mechanisms inside there. So retention depends on retention time, of course, when you're going to read these things. And this is especially problematic in MLC flash because threshold voltage window to determine the stored value is smaller, as we've discussed. So this is what we're going to do. Basically, this is what happens to a page over here. You start, you program and erase, one cycle, you program erase again, program erase again, program erase again, and after some point you cannot program or erase or read. And that's when the page dies. So this is, you erase a block and you program a page and you program the entire thing over time maybe, and then after the cell is programmed, it's subject to retention, and we're going to test different things. We're going to test a small amount of retention, a large amount of retention, how long, what is the distance between the time you programmed and the time you're going to read the page. So you get erase errors over here, you'll get program errors over here, you'll get different retention errors over here, read errors over here, and different sort of retention errors over here. So what we've done initially was, at that time, this is 2011, actually 2010 or so, we characterized error rates of 3x and 2y nanometer MLC NAND flash. I always forget, is 3x 30 to 35 or 35 to 39?
30 to 30.
Okay, that's better, yeah. So x is the lower one, y is the higher one. So y is this 2y is 25 to 29, let's say nanometers. They don't want to tell the exact technology level, that's why we keep it this way. Technology node. Okay, basically we're going to characterize that, and we're going to quantify the raw bit error rate at a given program erase cycle. Raw bit error rate means the error rate that you get before error correction, before you employ error correction. That's a fraction of erroneous bits. And we're going to quantify the error correction capability and area and power consumption of various error correction code implementations. I'm not sure if I have slides for that, but the papers cover that. And as I said, as you increase the error correction capability, your area and performance overheads increase, and the benefits that you get will not be very high. So basically, we are going to identify how much raw bit error rate each code can tolerate, and how many program erase cycles each code can sustain as a result of this. So let's talk about these first 2 a little bit, and I'm going to give you some main characterization results. So there's certainly a measurement methodology. You can read this, but basically erase errors, you count the number of cells that fail to be erased to the 1-1 state, clearly, after you do an erase operation. Program interference, you compare the data immediately after page programming and the data after the whole block is programmed. Read errors, you continuously read a given block and compare data between consecutive read sequences. And retention is interesting because there are different retention times. You compare the data read after an amount of time to data written. And there are short-term retention errors. We look at them under room temperature, but long-term retention errors, for example, then you need to emulate. Meaning, if you want to look at the effects of retention time that's 3 years, clearly we're not going to wait for 3 years, because that's going to be a very long experiment. So what we do is we actually use heating to emulate the effect of long-term retention. And people have actually shown that Arrhenius equation, which basically predicts the error rate based on the temperature, holds over here. But I'd be happy to talk about that. The papers actually have that detail. Okay, so let me give you some characterization results. This is the initial results. You can read the paper for more detail, but basically, this is what happens. This is the curve. This is the program erase cycles, how many cycles that a block has been programmed and erased. And this is the raw bit error rate that you get. And this shows which errors are dominant. And it turns out, that's the first thing is raw bit error rate increases exponentially with program erase cycles. Raw bit error rates, you can see this is a logarithmic scale. And it's increasing exponentially with the programming erase cycles. That's not good, first of all, which means that as flash memory becomes written a lot more, your robot error rate increases. And this is the fundamental problem. If you want to maintain some endurance level, you want to actually ensure that your robot error rate stays lower, which means that you need to add ECC or do something about it. And the second interesting thing is retention errors are dominant. For example, if you want to read data after 1 year, that's the 1 year retention errors over here. That's this curve over here, the red one. Not the red one, the thing below the red one, the green one. You see that more than 99% of the errors that you have at a PE cycle of 10 to the 5 is mostly retention errors. The rest of the errors are, yes, there, but they're not very high. This is program interference, this is read errors, this is erase errors. So erase errors are actually relatively low, as you can see, but they're increasing also over time. But retention errors are the dominant. And if you actually want to read the data after 3 years, they're actually even higher. So actually all of these are retention errors. That's the first observation, which was actually very interesting at that time. Now it's not that interesting. But retention errors also increase with retention time requirement, as I said. So what is the retention error mechanism in flash? It's charge loss. It's nothing fancy. You basically lose electrons from the floating gate, and that causes retention errors. And it turns out cells with more programmed electrons suffer more from retention errors. And threshold voltage that you have is more likely to shift by one window than multiple. And that's hopefully obvious also. Basically what you have is you have stress-induced leakage current that you have ongoing constantly. And this is what happens. Your threshold voltage distributions shift to the left. And once they shift to the left, your read reference voltage doesn't work well, as you can see over here. And it's very similar to DRAM. There's value dependency in these errors. This basically looks at the value dependency of the retention errors. And it turns out cells with more programmed electrons tend to suffer more from these retention errors. So going from 0, 0 to 0, 1 is the highest fraction of the errors, as you can see. And those are the states that have more electrons, as you can see over here. And 0, 1 to 1, 0 is also pretty high, as you can see over here. And the remaining is, but clearly there is a value dependency because of the voltage level of the cells that you program them into. This is also similar to DRAM, right? If you remember. So there's a lot more data, and this is the paper. This is actually the first academic paper that has real data from real flash chips. A lot of the things that we've written over here was actually known to industry, and we knew that, but it was not known publicly outside. And we were lucky to have some industry collaborators who actually designed the state-of-the-art SSD controllers at the time, and they're still designing that, and they have enabled us to actually get to a stage where we were able to do these studies. This was actually fun. It's really interesting that not a lot of real data was present at that time. The industry had written some papers, but they really didn't provide a lot of information about real data. So I think this points to the importance of having real data in the field, and this has actually enabled a lot of other people to do research in the area. Okay, so let me finish the retention errors, then we'll take a break. So, okay, we figured out that retention errors are the most dominant errors. They actually limit the programming erase cycle. So if I actually go back over here, there's an interesting thing over here. So you can set your ECC capability to satisfy some retention raw bit error rate. So you can do the calculations. You can say my ECC is going to be 40 bits per 1 kilobyte block, and those 40 bits, assuming some distribution of errors, can satisfy a retention error rate of 10 to the minus 3. Right. Now if you do that, and if you have this information, you can say, oh, my ECC is capable of handling 10 to the minus 3, and I can draw this line over here, and I say, oh, I expect my flash drive to die after some number of PE cycles, assuming retention errors were the only errors in the system. Right. Of course, to be able to really do the study, you need to compound all of the errors, and you need to have a usage model. So if your ECC is 10 to the minus 3, and if 3-year retention errors are the only errors in the system, you can actually go up to 10 to the 4 programming erase cycles. So this is actually one way of setting how much ECC that you want if you actually have this information. Now you can actually develop ECC, error correction mechanisms, that satisfy a certain raw bit error rate. That's one way of using this data, for example. Well, it's very valuable. If you don't have this data, how do you actually set your error correction bits, error correction codes to achieve a certain programming array cycles? That's not so easy. It's actually art at that point. But now it's becoming more science. Okay. Okay, we talked about this. Now we have retention errors. How do you cope with them? Well, you can add ECC, but we already know that that's not a good solution to retention errors, right? Well, we have another solution, which is refresh. And we're going to do that. This is non-volatile memory, flash. And many people don't know that it's actually not refreshed, but now everything is refreshed in flash, especially in data center SSDs where things are powered on. Okay, the basic idea is we want to refresh periodically. You change the period based on the programming array cycle wear out. You refresh more often at higher programming array cycles. Because initially, there are not much retention errors. Retention errors are not a problem at lower. So if you go back to this figure is very telling actually. If your programming array cycles are low, your raw bit error rate is not that high. Basically, if your flash drive is not very used, that's okay. Even if your retention time is long, no problem, because your raw bit error rate is not high. But if you keep using your flash drive and if you have written a lot to it, meaning your programming array cycle count is high, then raw bit error rate becomes a problem. Meaning that if you haven't written to your flash drive, maybe you don't refresh it much often, but you start refreshing it more often over here, you start refreshing it more often over here, you start refreshing it more often over here, maybe you start refreshing it every hour over here, right? So that's the idea. The idea is to adapt the refresh to the programming array cycle count in your flash drive at higher P cycles. Of course, now how do you do the refresh? I'm going to talk about this. Refresh is interesting because retention errors, you lose charge. Refresh is really not writing some random data, right? It's really, you need to increase the voltages. It turns out you can actually do this in place, meaning that whenever you do programming of a flash page, you can increase the voltage, but you cannot reduce the voltage. If you can increase the voltage, in refresh you need to increase the voltage, which means that you can actually program that particular page you need to refresh in place without moving it somewhere else. So that's one of the ideas that's employed in existing drives actually right now, but that may not always be a good thing. Sometimes you may want to remap this particular page or all of the pages in this block to some other place. And we'll see the trade-off between them, because if you actually do in-place programming, increase the voltages, you're causing program errors to adjacent pages. But you're not causing programming array cycle problems because you're not remapping. If you're remapping, you're not causing program errors to these pages over here, but you're causing some other issues. So there's a trade-off between these. And this paper discusses that trade-off. It introduces how to do refresh in Flash. So let me go over the key observations. So we've already observed this. We want to limit the retention errors limit flash lifetime as they increase over time, and retention errors can be corrected by refreshing each flash page periodically, obviously. So the key idea over here is to periodically refresh each flash page, correct its errors using weak error correcting codes, and either remap it to a new physical page or reprogram it in place. That's the idea. So it's called correct and refresh. It's not just refresh, because you need to read the page first, correct the errors using some error correcting codes that you have, and then either remap it to a new physical page or reprogram it in place, meaning you increase the voltage levels. Of course, you do this before the page accumulates more errors than correctable by the error correction codes that you have. So you need to do it early enough. So the optimization that we have is you can adapt the refresh rate to the endured programming array cycles. You start without refreshing. For a year, for example, you don't refresh your flash drive, not a year. For the programming array cycle count, some number of programming array cycles passes. After that, you start refreshing. After some threshold programming array cycles, you start refreshing more. So there are two key questions over here. One is how to refresh. So how to refresh in DRAM is not a question, but in Flash is a question. And when to refresh. When to refresh is shared with DRAM. So how to refresh, you can remap a page to another one, as we've discussed over here. You can reprogram a page in place. That's what this paper introduces. Or you could have a hybrid of remap and reprogram, depending on what you want, how you want to optimize your error rate. And when to refresh, basically you can have either a fixed period like DRAM, not so good, or you can adapt the period to retention error severity. And we're going to do that. So basically, the proposal is to have a hybrid of remap and reprogram and adapt the period to retention error severity. So let's talk about this in-place refresh. This is also called in-place reprogramming. You can actually do this if you know your data values whenever you actually want to write a different data pattern to the page, as long as your different data pattern is always increasing the voltages. Right? But that's not going to be easy to determine, right? But refresh, you know that you need to increase the voltages. So this is the floating gauge voltage distributions for each stored value. We know about this. Retention errors shift these voltages to the left. And if you do incremental step pulse programming in place on the same page, you basically shift the voltage to the right, and that fixes the retention errors. That's the idea over here. The big pro is there's no remapping that's needed, no additional erase operations. The con is you increase the occurrence of program errors because while you're programming, you're affecting what's happening around you. And there's a trade-off. If you're introducing too many programming errors, this is not good. At that point, you need to switch to remapping-based refresh. And this paper discusses how to and when to switch to remapping-based refresh. Okay, that's the idea. So let's take a look at the benefit, actually. The benefit is actually very interesting. It's very telling. So this is a different amount of BCH codes. BCH codes are actually very famous codes, error-correcting codes. I cannot spell the last names of the last two people, but I know the first one is Bose. It's named after 3 people who developed these codes. But basically, you can read about them, and they've been used extremely heavily in flash memory. Now flash memory is actually transitioning into something called LDPC codes, low density parity check codes, but we can talk about that, and the paper that I mentioned talks about that a lot. But this is different error correction capabilities you have, and these are different mechanisms. Baseline is no refresh, and this is the normalized lifetime. One is basically 512-bit BCH codes. At that time it was reasonable. And basically you have one over here that you cannot see, but that blue bar over there is 1. And this is what happens if you use remapping-based refresh. This is what happens if you use hybrid refresh. And this is what happens if you actually have adaptive hybrid refresh. Adaptive meaning adapt to the lifetime that you have. So as you see, base no refresh, if you go from 512 byte codes to 32K byte codes, yes, you gain some lifetime, about 4x, but it's not a lot. If you do adaptive rate refresh, you actually increase the lifetime by about 46x, which is a lot, which is good. And lifetime of FCR is much higher than lifetime of stronger ECC. So if you strengthen your ECC, that's not a good way of dealing with retention time errors, because retention time errors actually increase exponentially with lifetime. That's the problem that you're facing. And if you want to, you need to really increase your error correcting capability exponentially, and that's not sustainable. Even if it buys you something, and that something is relatively low, that low increase in lifetime comes at very high complexity. And the paper actually analyzed the complexity of ECC, but I'm not going to go over this right now. So it's very clear to everybody right now that ECC is not a good way of handling these errors. As I mentioned earlier, if you know your error mechanism really well, design a correction mechanism that adapts to your, that's a good fit for your error mechanism. Retention errors are not random errors. Retention errors happen because things shift, and you can actually easily fix them by refreshing. And okay, this is another thing over here. Basically, there's always a question, of course, what is the energy overhead of refresh? This is the energy overhead if you do it every year. This is the energy overhead if you do it every 3 months, every 3 weeks, every 3 days, and every day. So even if you do it every day, which is close to the end of the lifetime probably of flash, it's not that bad. And if you do hybrid refresh, it's even better. Remapping-based refresh causes a lot more energy overhead because you're remapping pages. And you can imagine how much energy overhead flash is causing in your system because it's always remapping pages, but you don't want refresh to add more to it. So initially, you're not going to actually refresh a lot. As a result, initial overheads are not large, but as your flash becomes older, written more, older meaning written more, then you need to refresh more. And this is a paper that goes into more detail. And this is, as far as I know, all of the industry-grade SSD controllers implement something very similar to this. They actually refresh flash memory. USBs, good luck. So there's a huge variety in terms of flash memory also, and its quality as well as the controller's quality. The industry grade, like data center grade SSDs that are dedicated and that are expensive do a lot. And of course, one of the downsides that the paper discusses, if you want to be able to do this, you need to be powered on, right? Your SSD needs to be powered on to be able to refresh clearly. Okay, and this is an extended version of the paper actually, which appeared at the Intel Technology Journal, which usually is restricted to Intel folks, but they were nice enough to invite us to write a paper at the Intel Technology Journal. So I'm happy about that. Okay, so we're going to talk about more errors, but I think it's probably a good time to take a break right now. Let's take a short break for 8 minutes, and then I'll spend 20 more minutes discussing flash memory errors. So let's be back at 1440. Okay, let's continue, since we don't have a lot of time. And this is such an exciting topic that we could spend days and days on it. But we're not going to do that, because there are so many such topics, right? Okay, so we've covered the retention errors right now, but as I said, there are many, many other errors. So let me give you an overview of some of these errors. If you're really interested, this paper actually does a lot of justice to these errors. Let's talk about the threshold voltage analysis and program interference. So basically, one of the other key questions that we have is, that we had next, is how does this threshold voltage distribution of different program states change over a flash lifetime? And can we model it accurately and predict the threshold voltage changes before they happen? And can we build mechanisms that can correct for these threshold voltage changes, thereby reducing read error rates? Perhaps one other way of handling retention errors is by changing the read reference voltage. That's not the best option, but that could be handled that way. Okay, so this is real data from 2Y nanometer chips using the read retry mechanism. So we are able to characterize the threshold voltage of different states, as you can see over here, at different programming array cycle counts across the device. And the device does vary leveling, so 1K cycle count meaning it's leveled across many flash blocks and flash pages. So this is the threshold voltage distribution that we had seen before in cartoon, but this is the real measurements from real devices. So as you can see, there's the probability density function. It's normalized. We don't give out the voltage values because they're proprietary. But you don't see the erase state because its voltage is somewhere over here, and it's not measurable actually. But if you look over here, it looks like a nice distribution. It's actually, we modeled as a Gaussian distribution with additive white noise. Keep that in mind. We're going to change that later on. It looks Gaussian, but that was a good model, but actually over time things change and we'll see different models. So this is the threshold voltage distribution at 1K cycles, 3K cycles, 8K programming array cycles, 15K. So as you can see, as the number of programming array cycles increases, the threshold voltage distribution's shape changes. It shifts to the right and it becomes wider. That's interesting, and for the reasons you can read the paper. But basically, there's a lot of variation that happens because of programming, erasing, retention, and a lot of things. And as a result, the distribution, different cells get affected differently, and there's a huge variation between the cells. As a result, you get this widening of the distribution over time. And because you're doing programming over time, your voltages actually tend to increase over time. So that's what it looks like. And also, as you can see over here, now distributions start overlapping, right? So it's not nice. Okay, so that's one example. So basically, we concluded at that time that the threshold voltage distribution can be modeled with relatively good accuracy as a Gaussian distribution with additive white noise. Basically, you can model the distortion in the threshold voltage distribution over programming array cycles as an exponential function of the programming array cycles. This picture doesn't show it, but the paper actually shows that the way the mean and the standard deviation of the Gaussian distribution changes exponentially with the programming array cycles. Which means that at programming array cycle X, you can predict the mean and the standard deviation of the same distribution after some time. Right, at programming array cycle 15K, for example. Now, if you know that, if you can do that, that's good. with more than 95% accuracy, now you can actually shift your threshold voltages. Right? You start with some threshold voltage at 1K cycle. You predict that it's going to be, okay, this much at 3K cycles. So when you're reading at 3K cycles, you use a different threshold voltage that you predict to be at that time. And while you're doing that, you actually calculate the real threshold voltage that you want to have. And then you use that. And basically, you can keep verifying your model online as well. So that's very interesting. And existing flash controllers do a lot of this, actually. And Gaussian distributions, not enough because it's only 95%. You want to be even more accurate if you want to minimize your orbit error rate. Because if you have a lot of bits, 95% is actually small. It's very similar to the branch prediction argument that we had, right? You may have, I don't know, 10 terabytes. And what is 95%? So you get actually, if your orbit error rate is even small, then you have a problem. Okay, if you want to read more, you can take a look at this paper. So later we actually realized that you really want this threshold voltage distribution prediction to be online and as little overhead as possible. And also, with smaller devices, this threshold voltage distribution becomes even harder to model. So this is a more recent paper that looks at essentially 1x nanometer devices, much smaller devices. And the distributions don't look as nice as you can see over here. This is, I don't know if you can see this very well. I don't know why my resolution is not very good. This is a very nice figure, actually. The projector is not doing justice to it. It's from this paper. But basically, if you look over here, these larger dots over here are actually the measured values. And the lines over here are Gaussian-based models. Those are the solid or dashed lines. Those are the Gaussian distribution, if you model them somehow. And you see that the Gaussian model is not terrible at 2.5 programming array cycles, but it's not very good also. So it cannot actually model this part. And there are weird effects, as you can see, right? There's this part over here. That's a P1 state, and it happens to overlap a lot with P2. So there are a lot of overlaps. And this is the scaling problem flash memory had, essentially. There are a lot of overlaps between the distributions. And that overlap increases, as you can see, at 5 kPe cycles. There's a huge overlap here between the blue and green, and also between the blue and red, the purple. And the overlap keeps increasing. As you can see over here, at 20K programming array cycles, there are a lot of errors. That blue state has essentially threshold voltages across the entire span of the threshold voltage range. And that's the scaling problem. Now the question is, how do you correct for these errors, right? So first of all, you want to model the distribution really well. And so this is better modeling, basically. We looked at a bunch of different distributions. It turns out the student's T distribution, T-based distribution, is a very good one. I'll give you the accuracy numbers in a little bit. And then based on that, this paper developed some mechanisms to reduce the error rates. But you can see that this actually models things really, really nicely. You can track the distribution nicely. That's good. And these are some example error rates that you see, basically. Gaussian is actually not terrible. But again, the numbers are not, because the distributions overlap so much, even an error rate of 2.6% is not very good. And of course, you need to do something else about these overlaps, in addition to predicting how the distribution will change. Okay, so basically, we looked at different models. Normal Laplace-based distributions are actually very good, but they're very hard to implement in the flash controller. A lot of calculations are needed. So it turns out students' T-based distribution is relatively easy to implement in the flash controller, such that you can actually predict what will happen next, and its error rate is not that far off from the normal Laplace base. So we're basically within 1%. We can model these distributions accurately within 1% today. But of course, this becomes harder as you go down below 1x nanometer. Okay, so this is, what is this? Okay, so this is basically the threshold voltage distribution as predicted by our dynamic model. So the curves over here, the solid and dashed lines, are predictions that are done based on what we observed until 10 kPe cycles. We predict what should be the distribution at 20 kPe cycles, because that's essentially what the flash controller needs to do. And the markers over here are actually the measured values at 20 kPe cycles. So this is the prediction versus reality. And you can see that it's not terrible. I mean, it's good actually, but there is a shift So these dashed lines are prediction at 20 kPe cycles without knowing what happens at that time, only with the knowledge of these values. It's like this, and this is the reality. So the reality is a little bit worse than what we predict, as you can see. And that's exactly what the flash controllers do today. They predict the future and they try to figure out if the reality matches the future. Okay, so that's not too bad. And this is really the state of the art work in planar flash memory that looks at how do you model these distributions accurately and the applications of that model. And I'm not talking about the applications of the model, but we're going to talk about some of them in a little bit. Okay. Okay, let's talk about other types of errors. We'll talk about program interference. When a cell is being programmed, the voltage level of a neighboring cell changes unintentionally due to parasitic capacitance coupling. And this can change the data value that's stored, of course. This is also called a program interference error. This causes neighboring cell voltage to increase, meaning to shift to the right. So you're increasing your own voltage, but you're also increasing the adjacent cell's voltage. This is like disturbance errors, but it's a program disturbance. So once retention errors are minimized, using refresh, for example, these errors actually become the dominant errors. If you remember that picture, that program interference was the second highest error cause after the retention errors. So how do we program current flash cells? We already talked about this. You basically use this two-step programming method. Okay, you program the LSB first and MSB next. So what is the program interference? Basically, it's going to be similar to what we've discussed with RowHammer, except it's a very different error mechanism. You have a victim cell that gets affected by a lot of aggressors around it. And these aggressors are everywhere. Actually, all of these are aggressors, if you will. The good thing is, we want to look at how much each aggressor affects a cell. We're going to ignore this part because of the programming method that's used in flash memory. Usually, this gets programmed before this one. As a result, the programming of this word line doesn't affect the programming of this word line. Usually, programmers, the flash drive manufacturers program in an ordered way to minimize the effect of these interferences. So we're going to ignore these. We're going to try to model the change in the victim cell's voltage based on the programming of adjacent cells. So a traditional model actually that people have proposed and have been trying to use for some time was like this. Basically, this is the change in the victim cell's voltage level when adjacent cells are programmed. It's based on coupling capacitances and how much things are coupled to each other. You can see that if this changes by delta Vx, you have some coupling capacitance between this, and it's multiplied by 2 because it's a bigger, essentially it's a bigger effect than this one. But you can basically say that the delta V of the victim is a function of the delta V's of adjacent cells times the coupling capacitances of the adjacent cells. Now it turns out this is usually not accurate and requires knowledge of these coupling capacitors. So it's very hard to implement in general. So if you really know your chip very well, even then you may not know your coupling capacitances. So we wanted to actually have a more abstract model to do this. A new, more accurate and easier to implement model for program interference. And the idea is very simple. If you can empirically characterize and model the effect of the neighbor cell threshold voltage change on the threshold voltage of the victim cell, you can do better. Basically, you know the characterization, you know the results. Now you can fit the neighbor threshold voltage change using a linear regression model, or any kind of model actually, but linear regression works well, and find the coefficients of the model via empirical measurement. That's the idea. So basically, this is the change in the victim's voltage, and these are, it's really a sum of the changes in the neighboring voltages with some coefficients. And we want to learn these coefficients somehow based on the experimental data. And of course, there is the voltage before the victim's old voltage. We should really fix the quality of this projector somehow because it's really bothering me. Okay, are you guys bothered with this? This is really low quality, isn't it? Okay. This was not like this before, was it? Okay, it was not. So we should really find a way of, I don't know what has changed here. Predictability is important. Okay, so basically we can measure the voltage of the victim before adjacent cells get programmed, and we can also measure delta V of the neighbors. So we can actually measure all of these delta V's here. The only thing that we don't know is the alpha values. And once we do a lot of measurements, we can fit this model to something, or we can also learn over time, right? Basically, that's the idea over here. So what we do is we do feature extraction for threshold voltage changes based on characterization. That's the threshold voltage changes on the aggressor cell and aggressor cells and the original state of the victim cell. And we have a linear regression model, and you can read the paper for more details. And basically, we use maximum likelihood estimation of the model coefficients to figure this out. And then you basically come up with coefficients, and then it becomes interesting. So the interesting part is this picture actually after you do all of that characterization. So this basically shows the relative importance of different aggressor cells, relative effect of the different aggressor cells on this particular victim cell. It turns out the immediately above cell has the most interference. Whenever that is programmed, its effect is the highest. 58% means that, assuming that the voltage of this is affected by 100% with everything, this contributes to 58%. And you can see that other cells are actually important also. These cells, immediately diagonal neighbor cells, are the second dominant cells. And even far away cells have effect. Actually, the word line that's after the immediate neighbor has an effect in flash. And there's no reason not to expect that. That's true for DRAM also. Actually, I believe RowHammer has a similar probability, except it's not easy to measure these voltages. The beauty in flash is you can measure these voltages to some precision. And also, basically, far neighbor cell interference exists, and actually victim cells, VTH, has negative effect on interference. So the higher your threshold voltage is, the less likely that you're affected by your neighbors. That's the interpretation of this. So I like this figure a lot because it's very interesting. I would love to do this for DRAM, for example, but it's not very easy to do. Okay. Okay, so basically based on this, you can develop a new model for program interference, and the model looks like this essentially. So we're actually going to eliminate these also, because whenever you're programming the neighboring bit lines as well. So these things actually don't affect you that much. They do affect you, but in incremental step plus programming, because you're programming an entire page, you can take that into account and do the programming accordingly. That's why these cells that are next to you on the same word line are not that important. But this is important because once you actually program this, you cannot change this one unless you go back and reprogram that one, which causes a ripple effect because that also affects what's happening over here. So there's a problem, right? So these cells you can actually account for while you're programming the word line. But these cells are programmed after this victim cell, so you cannot do much about them other than understanding it. Okay, so this is the model basically, and we have the coefficients. And let's take a look at the accuracy of this. So what this picture is showing is, again, this is the chips, and this is the threshold voltage before interference that we have, and this is the threshold voltage after interference. If there was no interference, you should be on this line, x equals y line, right? Clearly there is interference. These are the measured results. So you can see that interference causes a shift to higher voltages. Okay. Well, I already said that, I think. This is measured before interference, this is measured after interference, and those are the red dots. And this is ideal if there is no interference. As expected, clearly there is interference in real systems. And interference causes systematic threshold voltage shift. But if you actually model it the way we did, you can actually adjust, you can actually predict. So basically the red parts, x and y, are now the threshold voltage measured before interference and the predicted with the model. And that's the model prediction. And this is ideal if prediction is 100% accurate. So it turns out our prediction is pretty good. Our model actually corrects for the threshold voltage shift because of program interference with about 97% accuracy, which is not bad. But of course, if you really want to be more accurate, you want to have an even more accurate model, right? Okay, there are many other results in this paper that discusses the program interference effects in MLC NAND flash memory, which I'm not going to go into. Okay, so what can you do with this model? I'll cover this and then we will be done. Basically, our goal is to mitigate the effects of program interference caused voltage shifts. So clearly, read reference voltage affects the raw bit error rate. As we discussed, you have a read reference voltage between two states. Ideally, you would like to minimize the bit error rate, and bit error rate is basically the area where these distributions overlap. That's what that says. If you select the read reference voltage to the crossing point, that's good. You minimize the bit error rate. If you select the read reference voltage to be like this, it's not good because that's not the minimum bit error rate that you can get. So there exists an optimal read reference voltage based on the distributions. And it's really predictable if the statistics, in other words, the mean and variance of these threshold voltage distributions are characterized and modeled accurately, of course. So the idea is to have optimum read reference voltage prediction. Basically, you start with some read reference voltage and distributions shift after some program interference or whatever effect that you have. And you want to predict that VTH shift such that you can adjust the read reference voltage to be this blue one as opposed to staying at the red one, which is not optimal anymore. So the idea is to learn this. This is called VTH shift or threshold voltage shift learning. This is done every some number of programming erase cycles, and flash controllers actually do this right now. You program some sample cells with known data pattern and test the threshold voltage. And you program some aggressor enable cells and test the victim threshold voltage after interference. And you characterize a mean shift in the threshold voltage. This is called program interference noise. I'm taking an example with program interference. Of course, there are many other effects that cause this threshold voltage shift. And to predict the read reference voltage, now your job is easy. Assuming you've done all of this, you have a good prediction for the shift in the threshold voltage. You take the default read reference voltage and add to it the predicted mean threshold voltage shift by the model. And this is true for different distributions. Different distributions shift differently, so you need to do it separately for ER, P1, P2, P3. Well, ER is usually not a problem, but everything over here, essentially. Hopefully that's clear, right? You basically predict how much you should shift the threshold voltage, read reference voltage, based on the threshold voltages you measure. And this is the effect that you get, basically. This is the number of programming erase cycles, and this is the raw bit error rate. If you don't do any read reference voltage prediction, your raw bit error rate is high. If you do read reference voltage prediction, your raw bit error rate after you adjust your read reference voltage is much lower. And that's consistent across basically all of the programming erase cycles. And let's do this study. Let's assume that you have a large BCH code. This is the acceptable bit error rate is 2 times 10 to the minus 3. This BCH code can tolerate that acceptable bit error rate, which means that you should not cross this point. You set your ECC. If you don't do read reference voltage prediction, you cross that point over here. If you do read reference voltage prediction, you cross that point over here. So basically, you improve your lifetime by 30% by doing read reference voltage prediction, which is really significant. And basically, you reduce the raw bit error rate by 64% also. And that paper also discusses these read reference voltage prediction. But the JSAC paper in 2016 that I mentioned also actually does read reference voltage prediction using much more accurate models. And that's the paper that I mentioned earlier. Okay, so if you remember, we were talking about a lot of things in flash memory, and these are some readings that I would recommend. We may assign them later on. But we were in the middle of discussing flash memory error analysis and reliability, and there's a lot more to do in this area. And remember, we were discussing read reference voltage prediction. Actually, we were discussing a lot of techniques that are implemented in flash controllers today. Contrast this discussion with the DRAM discussions that we had earlier, right? DRAM controllers are really doing nothing compared to flash controllers, if you think about it in terms of reliability, for sure. But these controllers are doing, basically everything that I'm going to discuss over here is pretty much implemented or is being implemented in flash controllers going forward. So read reference voltage prediction is something that definitely exists today. Basically, remember, we developed models for threshold voltage distribution. Threshold voltage determines the value that's stored in a flash cell. And you have a threshold voltage range, and you chop it up into smaller sub-ranges. Each sub-range encodes a data value, right? It could be in an MLC, multi-level cell NAND flash. It could be 000111011, right? 2-bit flash. But there are flash memories that are 3-level cells right now. It's called 3-level cells, unfortunately, but it's really 3 bits encoded in a voltage range. It's really 8 states. In a sense, it's 8 levels, right? It's not 3 levels, but it's 3 bits. And people are looking into encoding 4 bits within the voltage range, right? So this threshold voltage distribution is important to understand because that the read reference voltages you pick are critical for how many errors that you get when you're reading. And remember the voltage distribution. Basically, we wanted to mitigate the effects of program interference caused voltage shifts, but this is true for retention also, as we will see. So this is an example of threshold voltage distribution. We actually covered these slides. Let's say you have these two different states, state A and state B, and this is the threshold voltage distribution of the cells that are programmed into these state A and state B. Ideally, you would like to pick this as your read reference voltage, and that read reference voltage essentially crosses the distributions at the point where the distributions cross each other, right? And this is the bit error rate you get in that case. The cells that are over here are supposed to be in state B, but you read them as state A because that's the read reference voltage you pick. And the cells that are over here are supposed to be in state A, but you attribute state B to them because they have voltage that's higher than the read reference voltage over here. And this is your bit error rate as a result. It's the area underneath these distributions that are marked, as you can see over here. So if you actually pick the wrong read reference voltage, meaning that, let's say you pick this one as your read reference voltage, V prime ref, then you get a higher bit error rate because the area becomes higher in that case. So you don't want to pick this read reference voltage, which means that if the threshold voltage, if assuming that you started with this read reference voltage and the threshold voltage is somehow shifted to the left in this case, you want to be able to adapt to that shift. That's why it's important to predict that read reference voltage before the shift happens. So basically there exists an optimal read reference voltage, and it's predictable if the statistics of the threshold voltage distributions are characterized and modeled. So if at this point in time, the threshold voltage distribution you know, and if you can predict that it's going to shift by this amount after so many program and erase cycles, let's say, or after some number of effects, then you can actually adapt your read reference voltage to the threshold voltage distribution changes. And flash controllers actually do this. I'm going to give you a couple of methods related to this. So basically, this is what we would like to do, right? Whenever the threshold voltage shifts to the right in this case, so after program interference, remember, when you have program interference, you're programming some cells, and the cells that are around it get affected because of that programming. So the threshold voltages of those cells that are around shifts to the right. That's why this distribution is here, and this distribution shifts to the right after program interference. Which means that if you're able to model the voltages nicely, you would predict that shift from Vref3 to Vref3 prime. That's the idea. So how do you do that? You can learn. You do this every 1,000 program and erase cycles, let's say. Of course, there is some thresholding that happens in existing flash controllers. You program some sample cells with known data pattern and test the threshold voltage. And you program some aggressor neighbor cells and test the victim threshold voltage after interference. And then you characterize a mean shift in the threshold voltage distribution. This is called program interference noise. And your optimum read reference voltage prediction could be this, basically. You have the default read reference voltage plus the predicted mean shift by this model that you learn over time. And you can do this in the background, basically. Once in a while, you figure out what would be my shift. And you could actually do this in a finer granularity. You could say, for these different cells with different characteristics, I'm going to learn different functions or different models. That's perfectly possible because some cells may have, you don't want to do this necessarily, but there may be cases where you want to do this. Like some blocks may have some number of program and erase cycles, some other blocks may have some other number of program and erase cycles, and you may learn different models for them. And that could happen, because especially if you're partitioning your hot data from your cold data inside a solid state drive, you will run into this problem. And existing drives are actually increasingly going forward to partitioning hot data from cold data. We will see that at the very end of this lecture, actually. There are many reasons for it, some of the reasons I gave in the last lecture. But if you actually put hot data together, you don't need to refresh it, for example. That's another reason to do it. If all of the data that you keep touching that data, you're writing to it a lot, then you don't need to refresh it much. So there are good reasons for partitioning hot data and cold data separately from each other. And which means that if you do that partitioning, the threshold voltage shift will be different for those data with different characteristics. As a result, you need to learn the different models in a different way. Okay, so this is one example from the paper that I mentioned. If you don't do read reference voltage prediction, your bit error rate, raw bit error rate before error correction is pretty high. If you do read reference voltage prediction as proposed in the paper, whose mechanisms are really implemented in existing controllers, then you actually reduce the read reference, you reduce the raw bit error rate significantly, as you can see. And this is independent of the of how worn out your flash device is. Basically, this is good to do in general, because your threshold voltages shift. And if you remember, I've gone through this, but I wanted to go through this again because we're going to look at some even more sophisticated things. Basically, you have an acceptable bit error rate given that you've decided on an error correction code. Let's assume a 32 kilobit BCH code. Your acceptable bit error rate is 2 times 10 to the minus 3. If you don't do read reference voltage prediction, you reach that at this many PE cycles, programming erase cycles. But if you do read reference voltage prediction, now you correct, you basically reach the uncorrectable bit error rate after much longer. Basically, you improve your lifetime 30%. This is interesting. Basically, this shows that your ECC gets you only so much. If you actually have other error correction mechanisms or error reduction mechanisms, in this case, read reference voltage prediction, you basically make more out of your ECC. Your ECC has some certain capability. How you use it depends on how many errors that you really expose, that you really require to be corrected by the ECC error correction code mechanisms. And this actually goes back to our discussion that we had before. If you can correct the errors in a much simpler way than using error correcting codes, you'd better do that. As you can see over here, that's what we're doing. With the read reference voltage prediction, we're really getting rid of some of the raw bit errors, which means that we're not punting those errors on error correction codes. As a result, we're using the error correction codes for errors that are not really corrected easily with read reference voltage prediction. Make sense? Okay. So another point over here could be, okay, you want to have a constant lifetime, let's say this is 30,000 in this case, 30,000 programming erase cycles, or I'll pick this location over here. You want to have that constant lifetime. You could actually keep that lifetime over here, do read reference voltage prediction, and have much less ECC in the system. So ECC that satisfies a bit error rate that's smaller than 2 times 10 to the minus 3, let's say 1 times 10 to the minus 3, would be much less complex. So there are multiple ways of using this, basically. You could reduce the amount of ECC by keeping the lifetime constant, as opposed to increasing the lifetime, keeping the ECC constant. Okay, so you can play a lot of tricks, clearly. Okay, we already discussed that. And this is the paper. Some of these papers, or one of these papers, may be assigned at some point. Okay, and we said that it's important to accurately, for this to work really well, you want to really accurately model your distributions. And I've gone over this. This is becoming increasingly complex. As I've shown you last time, Gaussian-based models are not really working very well, especially with devices that have very small feature sizes. And this is real data from a device that has 1x nanometer feature size. And you can see that, so let's say at 20,000 programming erase cycles, you can see that this distribution pretty much spans the entire voltage range. So that's the difficulty of actually making flash work at very small scales, because you have very small number of electrons, you cannot control them really well. As a result, this particular state, I think that's program state 1, starts spanning pretty much the entire voltage range. It doesn't start out that way. It's not that good to begin with even, but it doesn't span the entire voltage range. But once you, this is at 2.5K programming erase cycles. Once you're at 20K programming erase cycles, it looks like this. Now, if you have a Gaussian model is not good at adapting to this sort of discontinuities, if you will, or multiple peaks in the distribution. As a result, you would not get this part of the distribution correct. In fact, you're not getting that correct in many cases over here. That's true for some of the other ones, but the blue one is the most severe one in terms of the inaccuracy in the distribution. So Gaussian-based models don't work well, so this paper proposed a simple model, students' T-based model. It's easy to compute online also, that basically tracks this much nicely, as you can see. There's still some not imperfections, but it's quite good. These dashed lines are the model. The triangles, I think, those look like triangles. Yeah, triangles are actually what's measured. Make sense? So it's beautiful, actually. If you're designing flash controller, you would know these distributions really well. Okay, so this is an example of the error rates. So with the Gaussian, actually, you have it's not terrible, but 2.6% is not, is still high compared to the student's t distribution. And there's also normal Laplace the paper discusses. The downside is this is much harder to compute. So its error rate is low, but it's much harder to compute. So this is the latency that you need for online computation of the distribution. So it turns out Laplace, normal Laplace is much worse. But you can read the paper for more detail. Gaussian is easiest, but it doesn't give you a very good error rate. So student's t is a good compromise between computation latency of the distribution online during online operation and the error rate that you get in the end. Okay. Okay, and this is actually if you do the prediction versus reality with better modeling, meaning you don't know the distribution at 20K programming array cycles, but assume that you've collected data during operation at 10K programming array cycles and every 2.5K intervals. Then you can build a model using this information to predict the distribution at 20K PE cycles, right? With mechanisms that the paper discusses, but you can also imagine what those are. And this shows the prediction. This is the predicted distribution, the dashed ones. And the blue, the triangles are actually the measured values at 20K. You see that this tracks reasonably well. Okay, and basically, if you actually look at the actual and modeled optimal read reference voltages, modeled means, again, based on the prediction that you do, you predict the read reference voltage, the optimal read reference voltage at 20K based on data that's available to you during these programming array cycles. And you look at how does that compare to the actual optimal, because you can measure the optimal actual at the end when you know the values. So the actual is actually the blue one over here, and the triangles are the student's t. So the triangles are actually not so bad compared to the actual. Actually, Gaussian is pretty bad, as you can see over here. So actually, you can predict your read reference voltages. These are VA, VB, VC that are separating the four different states relatively well. So what is the effect on the robot error rate? Basically, you can see that in some pages, so some pages are not affected as much. You can read the reasons for it in the paper, but some pages are affected a lot. So in this case, for example, Gaussian gives you a much higher robot error rate, whereas student's t distribution-based modeling gives you a much lower robot error rate. So to gain this much reduction in error rate, we do all of that work to model the distributions. But that enables a much longer lifetime, as you can see, right? So if your ECC is not able to correct over here, if its correction capability is over here, for example, you would reach that correction capability much later in lifetime if you're doing the distribution modeling in a much better way, much more accurate way. Make sense? So I gave you a lot of state-of-the-art research very quickly. Okay, and this is the paper that actually looks at that. It says to appear, but it's already appeared clearly in 2016. Yeah. Okay, so this is one application of threshold voltage modeling. And these are really, really interesting applications, actually. But what else can we do further? Any questions so far? Now we're going to look at really, really, in my opinion, very exciting techniques. This is a technique that we developed there in around 2013. As I mentioned, when we first started looking into this research, industry was ahead of us. But once we understood things, this is the first technique that perhaps is really new that got into the products relatively quickly. And our goal was this, basically. We wanted to develop a better error correction mechanism for cases where error correcting codes fail to correct a page. You failed, error correcting codes basically say, I have an uncorrectable error. What do you do? Can you be more intelligent at this point? So let's take a look at some of our observations. We're going to utilize the observations that we've seen so far. Basically, the immediate neighbor cell has the most effect on the victim cell when it's programmed. We saw this, right? When you actually program a neighbor cell, the immediate neighbor actually has a huge effect. The neighbor that's above you. And we use a single set of read reference voltages to determine the value of the victim cell when we actually read it. And the set of read reference voltages is determined based on the overall threshold voltage distribution of all cells in flash memory. Basically, all of the methods that we just discussed build an overall threshold voltage distribution. Overall meaning this is the threshold voltage distribution of all cells belonging to this state, or that I think was programmed to this state, right? And you have 4 states, as you know. So keep that overall in mind. So basically, if you make that distribution conditional on the adjacent cell's value, you can see that that distribution is very different now. So basically, the threshold voltage distribution of cells with different valued immediate neighbor cells are significantly different, because neighbor value affects the amount of threshold voltage shift that you have. So I'll show you an example of this. Corollary is that if we know the value of the immediate neighbor cell of a cell we are trying to read, then we can find a much more accurate set of read reference voltages based on the conditional threshold voltage distribution. Conditional meaning conditional based on the value of the neighbor cell. That's the idea. So let's take a look at an example. So this is our victim word line, let's say, and this is the aggressor word line. And if we're going to, at some point, read this victim word line, try to understand what's the data that we programmed into it. This is before the last page of the aggressor word line is programmed. Let's assume that you program this to the aggressor word line. The distribution shifts because you actually program stuff over here. You're affecting the distributions over here. And I'm exaggerating things, of course, over here, right? If you assume a single threshold voltage distribution, regardless of the value of the neighbor, this is what you would get. And you would pick a read reference voltage, hopefully, if your prediction is right in the middle. Now, if you knew more, what if your neighbor was 1, 1? Then these distributions look very different. So if you actually look at all of the threshold voltages of the cells whose neighbors are 1, 1, immediately above neighbors are 1, 1, the distribution looks like this. Make sense? Which means that your threshold voltage is, if you actually want to just read those cells, you can pick a threshold voltage that's over here, not over here. Okay, let's take a look at 0, 0. If you want to look at, this is the threshold voltage distributions of all cells that are programmed to, whose neighbors are programmed to 0, 0. And if the cell itself is programmed to state pi plus 1, it looks like this. Pi looks like this. Again, this is the distribution for all cells whose neighbors are 1, 0. The distribution of all cells whose neighbors are 0, 1. And this is the conditional distributions. And if you combine them, then you will get these big distributions. Meaning that if you actually know your neighbor value, you could use some read reference voltage that's much better. That would give you a much lower error rate. And that's the key idea over here. If you knew the immediate neighbor, then you could choose a different read reference voltage to more accurately read the victim cell that you're trying to read. So this is called conditional reading, conditional on the value of your neighbor, as opposed to using the overall distribution. You don't use this overall distribution. If you use the overall distribution, you use this read reference voltage. But if you knew your neighbor was value was 1, 1, you use this read reference voltage. If you knew your neighbor was 0, 0, you would use this read reference voltage. And if you knew your neighbor was 1, 0, you would use this one. If you knew your neighbor was 0, 1, you would use this one. Yes? Mm-hmm. Basically, only the immediate last value. That's why this works, actually. Only the last one that you write to the top matters. That makes sense, right? Okay. Okay, basically, using the optimum read reference voltage based on the overall distribution leads to more errors. Better to use the optimum read reference voltage based on the conditional distribution, i.e. the value of the neighbor. Because the conditional distributions of the two states are farther apart from each other than the overall distribution. And okay, we verified this with real data. So this is measurements results from some real chip. These are the overall distributions, as you can see over here. They look like this, although in this case, it's actually nice. It's not terrible. But you can see the distances that you have between the different states. And the variance is relatively high. Okay, anyway, don't worry about that. Basically, you have a small margin over here. But if you do the conditional distributions, this is the distribution of all the voltage distribution of all the cells whose neighbors are, let's see, 0, 0. You see a much larger margin, right? This is basically what I showed you earlier, cartoonishly, the real data from the real chips. So basically, if you use the overall distribution, this is the bit error rate you would get. If you use the conditional distributions, knowing your neighbor value, your bit error rate is an order of magnitude lower, based on the real data from real chips. And that's the idea over here. So that's the idea that's called neighbor-assisted correction. It's called correction because you don't do this all the time. If you do this all the time, it's not good because you need to read a page multiple times because the neighboring page has many values. So you would need to do it, read multiple times. So you first you read a page with the read reference voltage based on the overall distribution, same as today, and buffer it. And if ECC fails, then you take action. Because if ECC fails today, you don't do anything, your drive is dead. If ECC fails, now you read the immediate neighbor page. And once you know the immediate neighbor page, you know the values in the immediate neighbor page, hopefully at least somewhat correctly. ECC might fail over there also, which leads to a recursive problem actually, but that's okay. Assume that ECC doesn't fail over there. Then you reread the page that you were trying to read using the read reference voltages corresponding to the voltage distribution, assuming a particular immediate neighbor value. Let's say you pick 1, 1. And you replace the buffered values of the cells with that particular immediate neighbor cell value, basically after this reading. So basically you just reread the cells that have an immediate neighbor value 1, 1, and then you basically replace them in the first read that you had. Hopefully you got the read correct. You apply ECC again. If the ECC doesn't fail, that's good. You basically corrected those cells whose neighbors were 1, 1. Now, if the ECC fails again, what do? You go back, you reread the page, and then you assume some other neighbor value. Let's say 0, 0. And then you replace them, and then you apply ECC again. Now you can actually correct. Basically, you do this 4 times in the worst case to cover all of the neighbor values. And eventually, you may be able to correct, or ECC fails, which means that you don't have any option. At that point, your drive is dead. So basically, it's an iterative mechanism. You read the page first. If ECC is correct, that's good. If ECC is not correct, then you start the neighbor-assisted correction process, which is over here. You read the LSB and MSB neighbors, and then you reread the page again with the read reference voltages, assuming a particular neighbor value. You correct the page. If ECC is correct, then that's great. You send the data out. If ECC is not correct, then you try this neighbor-assisted correction again with a different neighbor value. And if no neighbor values are left to try, then you give an error. And if your ECC is not able to correct anymore. That's the idea over here. Okay, we already said this basically. You read the neighbor values and use corresponding read reference voltage in a prioritized order until ECC passes, or if everything fails. Okay, there's of course questions over here, like how do you select the next local optimum read reference voltage? Yeah, you need to have that somewhere recorded. You need to learn that also, but I'm not going to go into the details. The paper has all of these details. Okay, so what is the benefit that you get? This is a bit harder to read over here, unfortunately, but if you don't do neighbor-assisted correction, this is your robot error rate curve, the red one over here. If you do neighbor-assisted correction with, and this is programming erase cycles as usual, if you just fix one value, which is 1, 1, you basically get significant reduction, and if you keep fixing more, you get more reduction in error rate. So let's assume again that your ECC is capable of doing this. This is achieving correcting a robot error rate of 1 times 10 to the minus 3. And you could achieve that by having an ECC error correction code bits, 40 bits per 1 kilobyte blocks. There's a period of your lifetime where you don't do neighbor-assisted correction. And after some point, your ECC starts failing. And there's a period of lifetime where you do neighbor-assisted correction by fixing just one immediate neighbor-based values. And there's another period where you do more sophisticated neighbor-assisted correction, another period where you do even more sophisticated neighbor-assisted correction. So you can see that with the first stage, if you do the simplest neighbor-assisted correction, you get about 22% lifetime improvement. Now, if you want to do more, you get even more lifetime improvement. So it's about 39%. Of course, this comes at the expense of latency, right? Because you read the page again. So it turns out you get pretty much no performance loss if you do go up to here. Well, there is some performance loss. It's in the paper, but it's within 1% or so. So if you start going into this part of the lifetime, then your performance loss increases. And you can see that there's some analysis in the paper, but I'm not going to go into this in detail because it has some other assumptions over here. Okay, Make sense? And that's the idea over here. And this is implemented. This is state of the art in many solid state drives today. And even 3D flash memories are implementing things like this going forward. Okay, so I've given you some really interesting stuff. So if you understand your device, you can do a lot more, as you can see. And as you can see, this is a very intelligent memory controller, right? This is really has a lot of intelligence in how it really treats the reading. If there's something like this in DRAM, that would be very good. Of course, we don't know how to do this in DRAM yet. Okay, so let's talk about some other areas in flash memory. We talked about RowHammer in DRAM, but as I said earlier, this type of error exists in flash memory or any type of memory. So we're going to look at read disturb in flash memory. And as I said, all scaled memories are prone to read disturb errors, DRAM, SRAM, hard disks, and we're going to look at it within the context of NAND flash. And I've already given you this picture before, but basically, very quickly, whenever you want to read a page, you apply a very high pass-through voltage to all of the other pages in NAND flash. And I'm going to go through this quickly because you know that, and we already know this as well, right? Basically, you encode data with threshold voltage value, and you distinguish between a 1 and 0 by applying that threshold voltage or read reference voltage. So if your read reference voltage is higher than the threshold voltage, you pass the value. If your read reference voltage is lower than the threshold voltage, the transistor turns off. You basically inhibit the value. That's how you distinguish between a 1 and 0. Okay, and pass-through is basically if you apply a if you want the cells not to affect what's being read from the top, you apply a pass-through voltage, which is higher than any of the read reference voltages, right? Which is really higher than actually any of the programmed threshold voltage values, not just read reference voltages. So in this case, 5 volts, let's say. So it's a very high voltage. So this enables reading, that pass-through voltage. So let's take a look at that. So if you want to read the values on page 2 over here, you want to apply the read reference voltage over here. Let's assume that you store 1 bit. And you pass through all of the other pages, meaning that you apply the pass-through voltage to all of the other pages. Now, what does this do? If you apply 5 volts over here, all of these pass through. So that's why they're green. If you apply the read reference voltage over here, the values, the transistors that have threshold voltages greater than the read reference voltage are inhibited, and other transistors that have threshold voltage values that are less than the read reference voltage pass through. As a result, you get this, and this leads to 0011, which is exactly what you want to read from that page. Make sense? Okay. Now, the read disturb problem happens when you repeatedly read from some page or any other page than page X, and the values on page X are disturbed because of that reading. Why does this happen? Basically, let's assume that you're reading from page 3. You apply the pass-through voltage to all of the other pages. And let's assume that you keep reading from page 3. You apply pass-through voltage to everything else, meaning that this application of the pass-through voltage has a weak programming effect, meaning that it shifts the threshold voltage of some vulnerable cells little bit. So this was the initial values that we have over here. And after doing this read disturb many, many times, the threshold voltage happens to shift to 2.6 volts. Very little, but it does shift. Now, if this shifts to 2.6 volts, let's assume that you want to read from page 2 now. Now, if you read, that's not good, because you get an incorrect value over here, because this value changed because of the read disturb that happened to it. And in this case, the read disturb problem actually is worse because you're affected by not just your immediate neighbor, you're affected by anything that's read in this particular block, right? Any page that's read. Because whenever you're reading a particular page, you're applying a very high pass-through voltage to all of the other pages in the block. That's how it works. That's how it's different from the RowHammer effect in DRAM. It's a different error mechanism. Okay, so here now we have a problem. We have incorrect values in page 2. This is the incorrect value. And if your ECC cannot correct it, then you have a problem. Your drive fails earlier, right? Okay, so basically let's talk about how to fix this problem. So it's actually, read disturb errors limit flash memory lifetime after you correct for other errors, like refresh. If you do all of the right things in your threshold voltage distributions, try to pick the optimum read reference voltage, get rid of the retention errors as much as possible with intelligent refresh, read disturb errors become the next problem. And they limit your lifetime because you apply a high pass-through voltage, as we said. Okay, we said this already. So this work actually characterized the read disturb on real NAND flash chips, and there are two ideas here. One is one of the observations that if you slightly lower this pass-through voltage, you greatly reduce the read disturb errors. So if you can get away without applying this very high pass-through voltage, you can reduce the read disturb errors. And also, some flash cells are more prone to read disturb. Some flash cells are less prone. If you can identify the cells that are more prone versus less prone, you can do much better error correction or error recovery if your ECC fails. So we're going to look at two techniques. One is mitigating the read disturb errors online by tuning the pass-through voltage. So we were tuning the read reference voltages. Now we're going to tune the VPass and dynamically find and apply a lowered VPass per block on a per block basis. And you can improve flash lifetime by 21% if you do that. So everything helps, actually. But if you keep adding these 21% everywhere, you get to a much longer lifetime. And the second technique is actually recovering after failure to prevent data loss. It's similar to neighbor-assisted error correction, but it's actually much more heavyweight than neighbor-assisted error correction. Basically, you selectively correct cells that are more susceptible to read disturb errors after your ECC fails by doing some probabilistic analysis of which cells are more prone to these read disturb errors and which cells are less prone. So we'll see this. This is actually really interesting. There's a lot of probability that goes into flash drives today. And I'm not even going to talk about the low-density parity check codes, which do some soft decoding that's very probabilistic to begin with. Okay. So this also reduces your orbit error rate significantly. So okay, let's take a look at this. This is an example. This is actually, again, real data from real devices. This is your read disturb count on a block, and this is a measured orbit error rate. And this is what happens if you apply different pass-through voltages. And let's assume that this is the tolerable orbit error rate over here. So if you apply the 100% pass-through voltage that's applied today, which is basically the highest level, 5 volts, let's say, your orbit error rate looks like this. You reach the uncorrectable bit error rate very quickly. In other words, your tolerable read disturb count is very low if you pick this pass-through voltage and if you pick this ECC. Right? You basically have a tolerable read disturb count that's less than 10 to the 5, less than 10,000 read disturbs. Now, if you actually lower the pass-through voltage a little bit, you start the curve starts shifting right, as you can see. If you lower it to 94%, the curve is over here, which means that your tolerable read disturb count is much higher. It's about more than 10 to the 7. Right? So that's the idea. If you can use a much lower, 6% lower pass-through voltage, you can actually reduce your orbit error rate significantly. And you can have much more read disturb count that you can tolerate. And that's the idea over here. So this is another way of looking at the curve that I just showed you over here. This is the percentage of reduction in the pass-through voltage, and this is the normalized tolerable read disturb count. So it goes to 1300x over here if you reduce it by 6%. Of course, if you keep reducing it, it's an exponential curve. It increases. But this is not a bad tolerable read disturb count. 10 to the 8 is you read from the same block, let's say 10 to the 8 times. That's not bad, right? It's actually much higher than today's RowHammer counts. Today, you can induce RowHammer in DRAM after 20,000 activates or so, depending on, of course, your DRAM. We don't want to be here, clearly, because this is not so good, but 10 to the 8 is not bad. Okay, so the first observation is that slightly lowering VPass greatly reduces read disturb errors. So how do you actually take advantage of it? So the idea is very simple. Once you know this, you tune the VPass. You dynamically find and apply a lowered VPass. Of course, there are advantages and disadvantages to it. You allow more read disturbs if you lower the VPass, but you can induce more read errors, right? If you lower the VPass too much, let's say you lower it to 4.94, and some cell has a threshold voltage 4.95. Now you get a read error on that cell. So you want to be careful. Okay, well, I guess this shows what I'm just going to say. Let's assume you reduce the VPass to 4.9 volts over here. This is good in this case, right? There's no problem. But if you reduce it to 4.7 volts, you have a problem over here. This cell is incorrectly read because it has a threshold voltage that's 4.8 volts. And if your ECC is not able to correct this, then you have a problem. But we're going to take advantage of the unused ECC capability, as we call it, to be able to do this. Because actually these high voltages are not good for many reasons. You want to actually reduce the high voltage as much as possible in a system. And what I'm going to show you is going to have benefit beyond just tolerating read disturbs, but reducing the high voltages is useful. So, okay. So what does this unused ECC capability mean? So you have an ECC limit, basically, and your ECC can tolerate some row bit error rate. And you set your ECC to be able to tolerate that row bit error rate. But it's really over-provisioned. Your ECC correction capability is not always used. There's some unused ECC capability, especially when you have a retention age that's low. You program the cell, and it hasn't retained data for years yet. It's retained data. You programmed it, let's say, 2 hours ago. At that point, your ECC is over-provisioned for that particular block, let's say, because there's not enough age in that particular block. Which means that you have unused ECC capability that's higher over here, that gets lower as the block stays in the flash drive for longer. And you can use that unused ECC capability to fix other errors that you may have. And in this case, we're going to induce more read errors to reduce the voltages. And we're going to fix those read errors by using this unused ECC capability. So actually, this is actually really interesting because this is a very general mechanism. If you have some unused capability in ECC, you can use it for inducing more errors to get rid of some of the other errors. And that's the idea, basically. And as I said, unused ECC capability decreases over retention age over here. So we want to dynamically adjust VPass so that read errors fully utilize the unused ECC capability. And we get rid of, we want to we reduce voltage as much as possible. So basically, as opposed to today's systems where you conservatively set VPass to a high voltage, you get no read errors, but you accumulate more read disturb errors at the end of each refresh interval, plus you have very high voltages to operate, which affects your energy consumption too. We want to dynamically adjust VPass to unused ECC capability. We're going to minimize the read disturb errors, and we're going to control the read errors to be tolerable by the error correction code capabilities. If the read errors start exceeding the capability of the error correction codes, then we start increasing the pass-through voltage VPass to correct the read errors. That's the idea. So you can do this in multiple ways. This is one example implementation. You perform once for each block every day. Let's say you estimate the unused ECC capability because you know when blocks are programmed. Flash controllers can have a lot of information. You aggressively reduce VPass until read errors exceed ECC capability. And if you gradually increase VPass until the read error becomes just less than ECC capability if you start getting errors. So that's the idea over here. You basically tune the VPass. And you do this once every day. And we evaluate this. You basically assume a 7-day refresh period. This works much better, of course, if you refresh your flash, right? If you don't refresh your flash for 3 years, then your unused ECC capability is very low. And that's one other reason for refreshing your flash once in a while. That actually gets you better use out of your ECC in the end. So not refreshing the flash is actually not a good solution because now your ECC is your ECC capability becomes much worse because your retention errors accumulate and ECC is correcting those retention errors. Refresh is a much easier mechanism to correct for retention errors. You don't want to use costly ECC to correct for errors that you can otherwise correct with simpler mechanisms like refresh. And every 7-day refresh is not bad, assuming you're powered up, of course, right? Maybe every 14 days is even better. If you remember last lecture, if you go to every day, now your overheads become increasing. But if you're every 7 days, refresh is not bad. Okay, so this is the overhead that you get. If you tune it every day, you basically need to spend about 24 seconds to do this VPass tuning for your drive, which may not be bad because there are cases where your drive is idle for 24 seconds, probably. That's true even for data centers. Okay, and there's some storage overhead, of course, to keep track of setting the VPass, and you can read the paper for that. So what is the benefit of this? So basically, the takeaway is average lifetime improvement is significant. It's about 20%, but it's very skewed. It's skewed in the sense that some benchmarks, some workloads actually over here, for example, for whatever reason, some of these are web servers actually, they do a lot more redisturbs. They read a page. Essentially, they do more hammering of a particular page for whatever reason. Some other workloads don't have that effect. As a result, you don't see significant improvements. But in these workloads, you see significant improvements in terms of lifetime. Okay, any questions? Am I going too fast? Sounds good? Okay, people are... Okay, you're learning a lot of really interesting techniques. I think this is really exciting, actually. And these techniques, I think, you can only find in the papers that I mentioned. They don't exist anywhere else. Or if you go and work and build your own flash controllers. Okay, so let's take a look at another approach to correct these redisturb errors. And we're going to take advantage of the fact that some cells are more resistant and some cells are more prone to redisturb. And we're going to develop an error recovery mechanism. And this error recovery mechanism will likely be an offline error recovery mechanism. It's because it's too much overhead to do this online during operation, as you will see. But offline error recovery mechanism is also very important because if your drive fails, you want to be able to get every bit out of there after your drive fails. Okay, so basically the observation is that some cells are redisturb resistant, some cells are redisturb prone. After applying the same number of redisturbs, disturb resistant cells, threshold voltage doesn't shift that much, whereas if a cell is disturb prone, its threshold voltage shifts a lot. So can we take advantage of it? So, which means that if you look at the threshold voltage distributions of, let's say, these two states, we can pick any state. Some cells, there's a heterogeneous set of cells in each of the distributions. Some cells here are redisturb resistant, some cells are prone. Also here, some cells are redisturb resistant, some cells are prone. Now, if you apply many redisturbs, let's say 250,000, this is what happens to the cells. The prone cells shift a lot, and the resistant cells, let's assume they stay where they are. And your threshold voltage distribution looks like this after that. Now we have a problem, right? Because now threshold voltage distributions overlap, and you have these cells that are mixed. This was initially in, this resistant cell was initially in P1 state. It stayed there. This cell was initially, let's assume this one. This cell was initially in the ER state, but it moved. Now they're close to each other. How do you disentangle them? Because this really belongs to state ER, and this belongs to state P1. But the observation is that disturb-prone cells have higher threshold voltages, so you can actually make use of this a little bit. And disturb-resistant cells have lower threshold voltages. You can actually make use of that also. So the problem happens here, basically. Whenever you do a read reference voltage over here, now you incorrectly read some of the cells. These are the disturb-prone cells. They should really belong to the ER state. And these are the disturb-resistant cells. They should really belong to the P1 state. Right? But here, if you look over here, you read some of them incorrectly. Okay, that's not happening. I don't know why it's not happening. My computer became, okay, Microsoft wants to auto-update things. That's why it's not happening. Okay, so basically, we misread these two cells in this case. But we don't want to misread those two cells. So how can we do that? The idea is taking advantage of the proneness, redisturb proneness of these cells to do error recovery. Let's assume you get an uncorrectable flash error. You back up all valid data in the faulty block. You disturb the faulty page, let's say some number of times, enough times, or many more times than 100K. And then you compare the threshold voltages before and after redisturb. Right? And then you select some cells that are susceptible to flash errors. Basically, these are the cells that are around this vicinity. Right? So, okay, basically, these are the cells that are around this vicinity. If you can somehow classify them as redisturb prone versus redisturb resistant, then you would actually say, oh, this one is redisturb prone, so I should really, this one is redisturb prone, so it should really belong to the previous state over here. It moved over here because it was redisturb prone. And this one is redisturb resistance, so it should really belong to the higher state. Right? That's the idea over here. If we can somehow probabilistically classify these cells, then we can actually switch the reading that we did and say, okay, I have more information, so I declare this to be in the P1 state, actually, because I know that it's read disturb resistant. Sorry. I declare this to be in the ER state because I know that it's read disturb prone, and I declare this to be in the P1 state because I know that it's read disturb resistant. That's exactly what we're trying to do. We basically try to figure out what is read disturb prone and what is read disturb resistant, and we select those susceptible cells that are likely to be misread, and you predict among those susceptible cells if the cells that have had more threshold voltage shifts, they're read disturb prone, which means that they should really belong to the lower VTH state to begin with. Okay, there's something wrong here. Cells with more threshold voltage shifts are not read disturb prone, right? They are read disturb prone, yes. Yeah, that's correct. That's incorrect. Okay. This always gets me messed up. Because once, actually, there was something incorrect in this slide, and I corrected it. But I'm not sure if this was the corrected slide or not. So, okay. So basically, you disturb the phage many, many times, and you figured out, okay, these cells are read disturb prone. Now, those cells that you're focusing on, this one's read disturb prone. And these are the susceptible cells. You say that, oh, I misread this. It actually belongs to this state. So you classify that as belonging to the lower threshold voltage state, ER in the previous case. And if you actually know that, well, after all of those read disturbs that you do, the cells that have less threshold voltage shifts are read disturb resistance, then you basically deem them as belonging to the higher threshold voltage state because they were susceptible. If you do this, now you actually reduce the error significantly. Of course, after you offline do this, we see that you can actually reduce the error count by 36%, and you can use the ECC to correct the remaining error. So you can actually put back your flash drive to be operational, if you still trust it, of course, after that point. But you can at least get your data out of it. So that's the idea over here. It's a probabilistic mechanism because it doesn't work, of course, and you basically probabilistically classify these cells. Okay, and if you really want to look at the data, this is the data that you see in the paper. And this is the paper if you're interested in looking at it. Okay, any questions? We made a lot of progress. We're still not at the end yet. But this may be a good time to actually take a break. What do you think? Any thoughts? Okay, let's take a break. Let's be back around 13 minutes later at 1:20, and then we'll continue. Okay, shall we get started? Looks like everybody's clustered on this side of the room. Is that the locality principle? We come from here, and then you're the more random access people. Okay, so we're going to continue. This is actually the first time I'm really treating flash memory as a full-blown lecture material, so you guys are lucky. This is really fun, I think, and there's a lot more to do in this area. I'm going to cover as much as possible, but we're not going to cover everything, of course. So we'll continue with the retention errors, because retention errors are actually still problematic, even after you do a lot of refresh. Some of the techniques that we're going to discuss are going to have similarities to other works, as you will see. And hopefully by now you will know some of the interesting things that are done in flash controllers. So retention errors are interesting because basically this is what we wanted to do. These are some presentation slides from the Flash Memory Summit, where we present pretty often, every year basically. So basically we want to understand the retention loss in real NAND chips and optimize and recover. Basically, this is essentially what you do in flash devices. I like the slide because for different types of errors, a flash device characterizes, optimizes, and recovers. Recovery doesn't always work online. It's sometimes offline. But optimization is very, very important. So we're going to especially look at read performance for all data over here, but relatively quickly. So this is one story that, this kind of story happens actually in flash device quite a bit. Basically, device performance degrades over time. By now, based on what you learned, this is not a surprise to you, right? Over time, you get more refresh, you try more of these error correction mechanisms, neighbor-assisted correction. As a result, your latency should increase over time, and your energy consumption should also increase. But there are some cases where things sometimes hit the news. I don't know whatever news this is over here, but basically, people talk about read performance degradation when the device gets older. And as you can see, reading old files is consistently slower than normal, as slow as, well, it's actually really slow, 30 megabytes per second, whereas newly written files are much faster, as you can see, right? Some important SSD of its time, probably from 2014, 2015 or so. Okay, so these things happen basically. These things happen because flash controllers actually optimize over time, and as a result, they may become slower. Hopefully, they don't become as slow as 30 megabytes per second in terms of bandwidth. But they do. And it's very fundamental. Basically, all data is slower because they have retention loss. This is nice slides from my student, Yishin, whose thesis was on flash memory, basically. I like the analogy here. Okay, so basically, you have charge leakage over time, and we know this, right? At some point, you get a retention error because you're depleted of charge, and you get actually wrong. Your read reference voltage basically doesn't give you the right value. And we know that this is one dominant source of flash memory errors. And one side effect is you get longer read latency because you adjust the threshold voltage to the shifts in the read reference voltage, shifts in the threshold voltage distribution. Okay, we know all of this. I'm going to go through this really quickly, basically. Yeah. And we can characterize it, as you know. So this is what happens. This shows the shifts in the threshold voltage distribution. So 0 day, meaning you programmed something, and at that point, you measure the threshold voltage distribution. It looks like this blue curve over here. After 40 days, that curve is the black curve. And this is still in a good device. If you actually keep going longer, the threshold voltage distribution shifts even more. Basically, the threshold voltage distribution shifts to the left and also widens because of retention loss. You're losing charge. As a result, your threshold voltage reduces, which makes sense. Okay. And basically, this is what happens, as we've seen before also. So at some point, your row bit errors become greater than the ECC correctable errors. At that point, you actually do something else, perhaps. This is what used to happen, actually, in the past. In the past, flash controllers were less proactive in terms of read-retry. Basically, your row bit errors are greater than ECC correctable errors. At that point, either your flash stops, flash drive is dead, or you adjust your read reference voltage. Today, everything is more proactive. Basically, you try to predict your read reference voltage, as we know. So basically, if you actually predict your read reference voltage, you hopefully shift it earlier. But assume that you didn't predict it well enough, you need to somehow increase your read latency, right? Basically, if you're in a really old device, and you get these row bit errors that are greater than ECC correctable errors, one of the first options for you to try is really to increase the read latency. Not increase the read latency, but change your read reference voltage at that point in time. Now, this is the downside of changing your read reference voltage at the point you're really trying to read it. That's why people have developed a lot of techniques to predict the read reference voltage before you really need to change it. Adjust your read reference voltage in a proactive manner. If you do it in a reactive manner, you increase your read latency at the critical path because you get these errors, you cannot correct them. At that point, let's find out our read reference voltage that works. That increased the read latency, and that's why you saw the news over there earlier. That's not a good approach. That's why we developed a lot of these proactive techniques. Okay, but at some point, you may need to do this. You still increase your read latency because your prediction may not be correct, and your errors may be too much also, right? So you basically want to try a good read reference voltage, and this, as we know it, this is read-retry. You basically change the read reference voltage, retry. If ECC passes, that's good. If ECC doesn't pass, you change the read reference voltage again, and try. Okay, so basically that's what happens. Over time, you leak charge. This generates retention errors. Even if you do refresh, this requires read-retry, and you get longer read latency. So the ideal read voltage, as we know, is basically the voltage that crosses these distributions over here. That leads to the minimal read latency. So in reality, this op changes over time due to retention loss. Luckily, you can actually model this also. So we're going to basically model this. this OPT, or optimal read reference voltage change, is gradual and unidirectional. It decreases over time. So if you want to adapt it to the retention errors, you can actually build a model for this. So the idea is very simple. Again, it's very similar to what we did with read disturb. But these are different components. Read disturb is a different type of error. Retention is a different type of error. Eventually, you need to build a model that encompasses all of those. And existing flash controllers actually do that. So one component is you online pre-optimize. You learn and record this optimal read reference voltage as much as possible. And you do this in the background once every day. So now you see that pattern, right? For these different errors, you do some background characterization once every day and predict what your voltage will be. And if your recorded optimal voltage is out of date, meaning that you use this read reference voltage, but you still get errors that are not correctable, then you do a read retry with a lower voltage. That's the idea. So what is the online pre-optimization algorithm? It's very similar again. It's triggered periodically. You find and record an optimal read reference voltage as a prediction per block basis. So basically, how do you find it? You actually do this characterization once in a while. Let's assume that this is your old read reference voltage. You basically find a new read reference voltage based on the characterization of the distribution. You do perform it in the background. So you get a small storage overhead, which is in the paper. It's similar to the read disturb mechanism. And if you want to improve the read retry, now you use this predicted read reference voltage. And this predicted read reference voltage is hopefully already close to the real optimal, right? Real optimal is really what you need at that point in time to minimize the errors. So if ECC fails, you decrease the read reference voltage and then retry. So hopefully now you don't do it. You don't do a lot of iterations in this read retry, right? That's the idea. That's why you need to model this predicted voltage. Okay. So if you want to look at it, you see actually a lot of benefits from these techniques. You can reduce the read retry count by about 30% if you do this modeling. And you reduce the decode ECC latency. You can optimize that also, actually, decoding latency. And you can actually reduce the total read latency significantly as well. Actually, this is normalized. So it's really 29% of what it was before, because you get rid of a lot of read retries. Read retry means, what does it mean? You read a page. If you want to read it with a separate set of read reference voltages, you read it again. It's basically doubling your latency if you do it twice. Basically, it's linear with the number of times you retry. That's why this reduction is very large. It's 70% reduction over here. This is normalized. And this is also 70% reduction in the read retry count. So, and it directly affects your latency, basically, as you can see. How many times you do the read retry. You don't want to do read retry that much. That's why you don't want to do neighbor-assisted correction that much also. Okay. So that's the idea, and we've already discussed this over here, I think. Yeah, you basically learn the optimal read reference voltage periodically, and then even if it's out of date, you minimize the read retry and the row bit error rate. Okay, we're going to look at another example over here. So if you know your cells really well, you can actually recover the data after failure too. This is going to be very similar to the read disturb prone, read disturb resistant cells. Similar to read disturb proneness, you have retention prone and retention resistant cells also. So we've already seen this. So, okay. Basically, there are some cells that are fast leaking, and there are some cells that are slow leaking. If they are subject to the same amount of time where they're not touched. And we can use this in a very similar way, as we discussed earlier. So these slides are going to be very similar to the read disturb recovery technique, right? If you look at these two distributions, P2 and P3, they consist of heterogeneous composition of slow leaking and fast leaking cells. Now, if you look at very old data, these distributions shift, and these cells get mixed, as you can see. Right? So as a result, this fast leaking cell, if you use the optimal read reference voltage here, this fast leaking cell that originally belonged to this distribution, P3, now is read as belonging to P2. And this slow leaking cell that originally belonged to P2 now is read as belonging to P3. Even if you use the optimal read reference voltage, even if you use all of the best read retry technique, you cannot fix this because you're really using the optimal read reference voltage at that point in time. So you need to use more information. What is that more information? That's exactly what I said, which is the fact that this cell is fast leaking and this cell is slow leaking. So your drive again fails because you have an uncorrectable error. What do? Well, you keep it around for a while. Basically, you record what you've read, and the drive has failed because of a particular read, clearly. You record what you read. Let's say you wait, I don't know, 100 more days. And then you figure out which cells are fast leaking and slow leaking. And then you do a statistical analysis saying, okay, this cell was fast leaking, so I misread it. I'm going to say that this is actually belonging to P3. And then you apply ECC again, and if it passes, now you recovered your data. Of course, the downside is you need to wait 100 days after your drive fails. But of course, you could do it after 10 days, 20 days. 100 days, you don't need to wait, I think. You can adjust that length. So that's the idea, basically. I already said this. Slow leaking cells have higher threshold voltage distribution. So there are some risky cells, as you can see, that fall into this vicinity where you get uncorrectable errors. And basically, this explains it. If you're a risky cell, and if you're slow leaking, you should really be characterized as belonging to a P2. If you're in the risky area, and if you're fast leaking, you should really be characterized as belonging to a P3. That's the idea. So how do you know whether it's fast leaking and slow leaking? Basically, you wait for a while and then do that. That's the fun way of doing it. Of course, that's not what happens. So basically, you guess the original state of the cell from its leakage speed property. You identify the risky cells, you identify fast, slow leaking cells, and guess the original state, and use that key formula. Basically, this is what we did for the particular evaluation that we did. This is one way of doing it. Let's assume that you program with random data. After 28 days, you detect some failure because ECC is not able to correct. You back up the data, and you wait for 12 additional days, and then you can recover the data correctly. And this eliminates a significant number of raw bit errors, and ECC can correct the remaining errors. Of course, it's not an online mechanism, right? I mean, you could potentially do it online, but you really need to know your access pattern extremely well. Or your access pattern needs to allow you to wait for 12 additional days. I don't know which access patterns do that. Okay, so that's the idea. And you can read the paper for more detail. You get significantly lower, shorter read latency with the original retention-optimized reading technique, and you can recover data after failure if you know your cells well. And that's the paper. Any questions? Okay, so I've snuck in the large-scale field analysis here very quickly. I'm going to talk about that. So we've been talking about very small-scale analyses right now, right? These are understanding your device. It's always good to know your large-scale field analysis also, and I'm going to give you an example. But we're not going to go into the detail of this that much. You should read the paper for more detail. So basically what we did was, we did the study with Facebook. Actually, a lot of the data center companies now use SSDs very heavily in their systems. And other people have done studies with Google and Microsoft flash memories as well. So these are correlational studies. You basically look at a very large number of devices and look at the error rates that you get in the field. So we cannot report the number of devices, but it's a lot. Tens of thousands, hundreds of thousands, maybe larger. Actually larger. But basically, this is the distribution that you get in the error rate of the device. It's very interesting. This shows that some devices fail a lot more than others. So there is a variation across the devices also. As expected, we've seen this variation in DRAM, right, in the past. And this follows a Pareto distribution. You can read the paper. So you could potentially make use of this data for predictive reasons also, but I'm not going to talk about that. But some of the things that we've examined is this. We looked at read disturbance, temperature effects, access pattern effects, life cycle, how do different SSDs behave. I'm not going to go through this in detail. You can read the paper. But there's an early detection life cycle period, which I'm going to briefly talk about. So do you guys know about the bathtub curve? This is very common. This is a fundamental curve. Oh, you know about it. Okay. In reliability, basically. It's not really related to electronics even. Any kind of part has this kind of lifetime pattern. This is when the part is manufactured and the first time you use it. And over time, as it gets used, the failure rate looks like this, if you look at a large number of parts. So initially, the probability of failure, or the failure rate across a large number of devices, is very high. And then this is called the infancy period. and then you become more mature, you don't fail as much, and then you become older, and you fail. So this is the wear out period: infancy, normal lifetime, and wear out. And that's very fundamental to many devices. People have done studies with cars, for example. Cars, when they're first bought, their failure rate is high because they're not tested. These are the ones that may not have been tested just enough, right? They fail very quickly, and the ones that survive are going to survive for a long time. It's actually a property of this Pareto distribution. If you survive long enough, the probability that you're going to survive longer is high. If you haven't survived enough, the probability that you're going to survive is not as high. That's called decreasing hazard rate. These distributions with decreasing hazard rate that have that kind of property. If you've survived, your hazard rate decreases. That's the idea. And this is actually, basically, this is a fundamental reliability curve. You have this bathtub curve. So we see somewhat this bathtub curve in the SSD distributions that we study. Well, this is the early failure period, useful life period, and wear out period. But it's a bit different, because part of the reasons we use a different metric. We use a time-independent utilization metric, which is the number of times you've written to the SSD. So this is what we see, basically. This is the data written, and this is the failure rate. And we need to do the study actually more right now. Basically, we see somewhat like the wear out curve like this. You have the wear out period, you have the useful life period, you have the early life failure period. But there's also this other early detection period that looks like this. Initially, you have a smaller error rate. But maybe that's too early in the lifetime to see this. I don't know. But you can read this in the paper more detail. There's some potential analysis in the paper that says maybe there are two types of distributions over here. Some devices actually are in the failing mode at this point in time. Okay. So temperature is very interesting also. So this is, again, a correlational study. If you look at an SSD, there are temperature sensors over here. And we look at basically how those temperature sensors correlate with the failure rate. And there are multiple different cases. So these are some SSDs where temperature positively correlates with the failure rate. In this case, as temperature increases, your failure rate also increases. Failure rate is uncorrectable error rate, basically. And you can read the paper for more detail as to exactly what this is. But it's correlated with your uncorrectable error rate. But there are some other SSDs where SSDs throttle themselves or shut down themselves if you have high temperature. And you get results that are temperature independent. So these are some other SSDs. You can see the manufacturers, A, B, C, D, E, in the paper. I recently presented a paper, and somebody said we should be putting out these manufacturer names as opposed to ABCs over there. And my response was, well, if you work hard enough, you can really figure out what those ABCD is, first of all. Second, if you ask us, we can tell it. But putting out those names is not very nice in a paper, especially if you want to sustain a relationship with those manufacturers. And this is really important, actually. We would never be able to publish any of those flash papers if we insisted on putting out the manufacturer name out there. I think sometimes people don't understand the difficulties in putting out real data out into the field. So it's very important to actually anonymize these manufacturer names when you put out real data. Of course, in some cases we don't, right? But those cases are not as sensitive as some of the data that we put over here. Some of these failure rates that we put out in Flash, for example, directly go to the heart of the manufacturer's business because they actually, these directly affect their yield. If you look at performance data, of course, performance data, everybody can measure, but some of this data is not really easy, something that everybody can measure. Okay, but you can guess, actually. If people do their homework a little bit, you can guess who ABC is. And in general, if you actually want to learn this information, you can get that information from the authors by asking them privately, as opposed to asking them to report this to the entire world. Okay, that's a side note, basically. So these are manufacturers. You may not know what they are, but that's okay. I mean, actually, these may be the same manufacturer, but different types of generations of devices also. So this is a more intelligent device, perhaps. It throttles itself. But of course, there's a downside. Once it throttles itself, it doesn't work as fast. and there's some analysis in the paper related to that also. So basically, the key takeaway is throttling the SSD usage actually helps mitigate temperature-induced errors. What does throttling means? Basically, you throttle the access rate. Sometimes you shut off, actually, SSD, which may not be really great for performance, but if you're operating at very high degrees of temperature, then that may be the right thing to do, right? As opposed to getting these huge number of errors that you see over here. Okay, so there are other observations over here. Read disturbance is an important problem, as we discussed, but read disturbance errors actually don't affect the software because there are multiple reasons. One reason is flash memory actually corrects a lot of these errors in the SSD. As a result, we do not actually see this. So this study is done at a high level, basically. We look at the software observable errors, meaning that these are the errors that are not corrected by the SSD, right? So there are multiple levels of error correction. So if you get error correction in the SSD, okay, you may correct it. That's fine. It's handled internally there. But there may be some errors that are not corrected by the SSD that get reported to the operating system. Now, the operating system has measures for correcting those errors also, right? It could have partitioned the data across different SSDs, for example. It could have a redundant array of an inexpensive disk space on system, where you actually have multiple copies of data in different parts of the SSD, and it could actually try to resolve the error using those techniques. So these are the errors that are reported by the SSD that may be potentially resolvable by the operating system. Okay, read disturbance doesn't make its way up to the operating system basically as much. Okay, temperature we already discussed, I think. And there's also, SSD also has page caching, right? Inside there's DRAM inside the SSD today, as we've discussed in the past. And it employs page caching. And it also employs over-provisioning to handle the writes in different ways. And the paper actually quantifies the effects of those, and you can read it for more detail. But I'm not going to go through this in detail. There are more studies to be done in this area. Of course, these are also hard studies to do for various reasons. One is getting access to this data is not easy. Big companies have access to that data, but they don't necessarily collect all the data. So we were much more lucky with the DRAM studies that we've done with Facebook, for example, because the data that's collected over there was much more comprehensive. The data that's collected over here was not so comprehensive. That's the first difficulty. The second difficulty is, okay, you have access to data, let's say, but you don't control the data. This is all a purely correlational study, right? So you cannot really draw very strong conclusions from these studies. You can say, okay, temperature correlates with failure rate. That's good. But you cannot, so correlation is not necessarily causation, although in temperature it's not bad. Maybe you can guess the reasons, but you cannot prove it, right? Whereas in the other studies that we've discussed, you can actually control only one variable, assuming you design the experiment right. Here, you're not designing an experiment. You're just observing what's happening in the field. And by nature, that's correlational. But it's really important to do these studies also, and you can, maybe some of you will do that. And there needs to be more of these studies, I think. We have these huge scale data centers in the world, and there's a lot of data to be collected, to be understood. I think the number of people who are doing these studies is too small compared to the amount of data that we actually have about these machines. Okay, I don't know what this is. So there are some other works that I'm not going to cover. This is actually interesting. This basically talks about some potential vulnerabilities in NAND flash memory and potentially exploiting it for security attacks. This is not easy, I think. Again, it's not easy because flash memory is not directly exposed to your programming language, right? You go through layers of operating system, file system calls, and then even after that, there's a controller sitting in between those requests that is coming from the system and how it handles those requests, right? So how do you actually bypass all of those to induce attacks? It's not easy, I think. But there's some vulnerability here. And this paper looks at the reliability as well as security issues of memory programming mechanisms. If you remember, we have different kind of programming mechanisms. If you want to program a multi-level cell, you do two-step programming, right? And that two-step programming actually leads to some vulnerabilities because you program some cells first, wait for a while, and then program some other cells. Okay, but if you want to learn about that, this is the paper to take a look at. And we've already discussed this one. Now let's take a look at 3D NAND a little bit. Any questions so far? Do other people find this as fascinating as I find it? Okay. I think it's really fascinating because emerging memory technologies are looking like this at some level. They're somewhere in between DRAM and flash. So if you look at emerging memory technologies like what we've discussed, phase change memory, there will be controllers that are doing some of this. And those controllers need to be even more careful than flash controllers because the latencies of those memories are much lower than flash memory. Yet you need to actually do a lot of error correction to make sure that they work also. And as a result, similar techniques are going to be employed in those controllers in a much more efficient manner. Okay, so let's talk about 3D NAND, because so far, actually, all of the data that I presented is from 2D planar NAND. And it's very interesting still, and it's going to be even more interesting, especially when 3D NAND scales down to smaller feature sizes. And at some point, flash manufacturers were actually very limited in terms of planar flash memory. And all of these error studies are extremely important, and they're still very important. But 3D NAND relaxed things a little bit and changed things a little bit. And we're going to talk about that, because it enabled another level of freedom, which is the 3D stacking nature. And we've actually done some studies. I'm not going to talk about all of them, but this is one. Yishin's dissertation was actually on both planar as well as 3D NAND, but his latest contributions were on 3D NAND, both error modeling as well as mechanisms to reduce errors, improve reliability. I'm going to talk about this one in a little bit. Okay. So basically, we have this lifetime problem. I think we see this before. Generation N looks like this. And this is an example. Raw bit error rate curve looks like this. And you have to achieve some, you have some ECC that achieves some lifetime, right? And if you go to generation M+1, even though you may actually increase your ECC capability, your lifetime becomes lower because this is much less reliable, right? I've shown this in a much different way earlier when we first started the flash memory lectures, but this is really the fundamental problem. You move from one generation to another generation, even though you may actually have increased ECC capability, you actually get less lifetime. And I've shown you the numbers for this very early on in the previous lecture, lecture 14B. Okay. Yeah. Okay, so basically, that's exactly what was happening with planar NAND flash memory. And that's exactly what the scaling problem was. And manufacturers reduced the flash cell size, reduced the distance between cells, and tried to have more multi-level cells to increase capacity. But this actually led to reliability problems. In 3D NAND, you could do all of those, but you also have another level of freedom, which is you can add more layers on top of it, on top. So you actually have this three-dimensional structure, which we will see. So if in planar NAND, scaling actually hurts reliability, scaling the cell size, reducing the distance, and also reducing the, chopping up the threshold voltage distribution to finer pieces to store more bits. They all hurt reliability, and we've studied that a lot. Now, this is not well studied, and we're going to change that now when we discuss this. So all of these that we discuss is applicable over here, but there's more. Now, the upside here is, what did the manufacturers do? This level of freedom provided them a breathing space, if you will. Now they're operating in that breathing space, where they don't need to reduce the flash cell size as much. Now they actually increase the flash cell size. So here it was about 15 nanometers, let's say. Now it's about 40 nanometers. They increased it, but they were able to put more stuff, have higher capacity by having more layers, like this. So that enabled improved reliability in some aspects, because you don't have some of these problems, at higher capacity. But that's a one-time jump. You move from 2D technology to 3D technology. Now 3D technology, as it scales, it's going to have problems. One is, how does it scale? You increase the number of layers. That leads to some problems, as we will see. Or you actually do very similar techniques, which all of those need to be done if we want to keep increasing the capacities. And as a result, we will see that 3D NAND flash memory is going to become even more complex than planar NAND, because it's going to have all of these issues that we discussed, plus issues caused by 3D. Okay, But it's still a good technology. I mean, it's a good move from one technology to another, but it's going to be more complex down the road. So this is, we've seen this before, but this is the charge trap transistor. It's a 3D structure. You have this control gate that wraps around this layer over here, and charge gets trapped inside over here in an insulator, and you have the substrate and the source and drain. Now you can see that you can stack these transistors on top of each other, right? And that's essentially what people do. Well, just to contrast, this was a 2D floating gate cell. There's a 3D charge trap cell. It turns out actually you have less charge over here. 3D cells actually can be floating gate also, but they're not as well studied so far. So floating gate is not, whether you have floating gate or charge trap is actually independent of 2D or 3D. But it turns out charge trap is easier to manufacture in 3D, and floating gate is a bit harder in 3D right now. But take that with a grain of salt, that's going to change. But this is what the structure, this is the fundamental structure of the charge trap cell. And you basically string together many of these charge trap cells in a 3D manner. This is what the 3D structure looks like. You have these bit lines, 3D, and then you have these word lines. Word lines are within a layer. Bit lines cross across the layers, as you can see. And a block is still the same as what we discussed before. It's bit line, word line. But a block now spans multiple layers, as you can see. Right? Does that make sense? And you have another block over here, another block over here that is completely separate. Good? Okay. Is there anything else that I want to say over here? I guess not. And then you, of course, have the sense amplifiers and everything else that is not drawn here. Okay, so I mean, there's more detail over here, but you can read this paper for some more detail. So now let's take a look at the comparison of some of these errors that we've studied. Program erase cycling, I'm not going to go into detail, but this is discussed in that paper, this paper that I mentioned over here. But program erase cycling, it turns out, this is wear out. 3D cells are less susceptible because charge trap transistors that are large are good for now. So this is not as big of a problem at the moment. But as the cell size scales down, this is going to be a bigger problem, as we discussed. Program errors, program interference errors, basically 3D is less susceptible again for now. Because the cell size is large, they use one-shot programming. They don't do this two-step programming that's really needed as the cell size becomes smaller. And as a result, this is also less susceptible. Cell-to-cell interference is also less of an issue in 3D because you have a larger manufacturing process technology. As I said, it's 35 to 40 nanometers as opposed to 15 nanometers, let's say, 10 to 20. Data retention is actually a bigger issue, it turns out. 3D is more susceptible in this case because you have this early retention loss problem. Whenever you program, after you program, you quickly lose data. So you need to have solutions to this. So retention loss, longer time retention loss is a problem in planar, but early retention loss is a big problem actually in 3D. And read disturb, again, is less susceptible because of the larger manufacturing process technology. So this is the breathing room that you see, right? The manufacturers got a breathing room because they were able to actually invent a new technology where they could manufacture much better. A lot of the error characteristics are better, but some of them are worse. But now if you go down, if you scale everything to a very smaller sizes, all of these errors are going to become more important again. So I'm going to go over one paper very quickly, just to give you a flavor of what are the things that are slightly different than 3D. I'm not going to cover the things that are similar. Basically, the motivation is clear, right? 3D NAND error characteristics are not well studied. Actually, these two papers that I just mentioned earlier are the only two areas that are with real 3D NAND flash devices that give you comprehensive data. So we wanted to understand and mitigate 3D NAND errors to improve lifetime. So basically, understanding requires characterization. So it turns out there are some conclusions over here. One is very interesting. You basically have huge effect of process variation across these different layers. So there is basically more than one order of magnitude error rate difference between layers. Some layers that are in the middle actually have very high error rates for various reasons. So that's one problem. Early retention loss is another problem. Error rate actually increases by 10x after 3 hours after programming. And this is much higher than actually planar. And there's also retention interference, which I'm not going to cover that much. It's not observed before in planar NAND. Basically, you have this retention loss interference problem that you can read in the paper. So if you actually know this, you can actually apply similar techniques. You can model the raw bit error rate and threshold voltage. So this paper develops a raw bit error rate variation model and a retention loss model for 3D NAND flash. But I'm not going to cover that in a lot of detail. The principles are relatively similar. It's a bit more complex in 3D. And also, how do you mitigate 3D NAND flash errors after that? So if you know that process variation is a problem, well, why don't you pick the different read reference voltages for different layers? If your layers have different threshold voltage distributions, it makes sense to have different read reference voltages for different layers. And that's the idea over here. And also, if your layers are actually very disparate from each other in terms of error rates, maybe you actually do better interleaving of your rate such that you pick blocks in a more balanced fashion. And I'm going to talk about that briefly. And also, there's retention model aware reading that basically adapts the read reference voltage to the predicted retention. And actually, if you do all of this, you can improve 3D flash lifetime by about 2x, 1.85x, or keep the flash memory lifetime and reduce the error correction code overhead by about 80% in this case. Again, you can play different tricks, right, depending on what you want to do. So let's take a look at this very quickly. I'm going to focus on the interesting characterizations. Basically, this is another look at the 3D chip, right? I didn't show it exactly like this before, but it actually looks like this. You have these different layers, and this is one word line, this is another word line, and this is the bit line, as you can see. And this is one block over here. This is another set of blocks over here. This third one is another, fourth one is another one. And that's a flash cell, as we know. So basically, these may have different error characteristics, and they do have different error characteristics depending on which layer you're at. And we did have some characterization methodology that you can read in the paper. So this is the layer number, normalized. And this is the raw bit error rate. And these are MSB and LSB pages. You see that there's a huge variation across the layers. The lowest layers are actually the ones that are in the lower bottom part. And the ones that are in the middle are actually susceptible to more more errors. Well, part of the reason is you're sandwiched in between, right? You really have a lot of effects going on because you're really affected by many layers if you're somewhere in between. And that's one of the explanations over here. Of course, there needs to be more characterization and understanding to understand this. But this is a real effect. It's measured across many chips. You have a significantly higher error rate in the middle of the stack. Does that make sense? Okay. Okay, and MSB and LSB has a difference also, but you can read the paper for that. And that's the maximum raw bit error rate happens in these layers in the middle. And other chips see similar trends. Okay. So there's a retention loss phenomenon also. You basically lose charge. Except in planar NAND, this happens to be a much slower process, whereas here, it happens to be a much faster process. Due to the properties of this charge trap, it happens to be very quick. So you quickly lose data. So this is an example of this. This is the raw bit error rate that you get, and this is the retention time. As you can see, this is much slower process in planar, and this is much faster in 3D. Basically, if you want to have 3 hours retention time, you get 10x more errors compared to the base over there. And you get 10x more errors if you want to have 11 days more retention time. And you get 10x more errors if you want to have 3 years more retention time. So you get a lot of errors, basically. But here, it's actually a lot. Early retention loss, that's why this is called early retention loss phenomenon. You accumulate 10x more errors very quickly in the very beginning, right after programming. Okay. So how do you, okay, I'm going to, and also there's another thing, amount of retention losses correlated with neighbor cell states. I mean, that's actually true for planar NAND, but it's actually much bigger effect on 3D NAND. So you need new mechanisms to tolerate these different observations that we just discussed. And there's more detail in the paper that you can take a look. So how do you actually develop new mechanisms? Well, we're going to develop new models. We're going to model the threshold voltage distribution of 3D NAND. And we're going to try to predict the read reference voltages just like we did. And we want to actually predict the row bit error rate as well. So there's a row bit error rate model in the paper. And I mean, these fundamentals don't change between 3D NAND and 2D NAND. You still have this sort of distribution, except that distribution varies across layers, right? And we want to do the same thing that we've done before. We want to predict these voltages. So this is the retention loss model. You can actually model the early retention loss as a simple linear function of log retention time. You can read the paper. I believe this is going to get more complicated as cells become smaller. So take all of these with a grain of salt. Your flash controllers need to adapt to the technology that they actually are built for. Okay. And actually, I'm going to skip a lot of this because this is basically the model, the optimal voltage prediction model. And you can see that there are a bunch of functions over here, like program erase, cycle count, retention time, and some parameters that are learned using regression, right? Okay, and the model there is actually pretty good. But you can read the paper for more detail. So if you actually have a model like this, you can predict the per page row bit error rate. And you can see that this is the model. Well, this is the fit over here. It's a gamma distribution. And this is the fit for variation agnostic VOPT. So basically, variation agnostic VOPT uses the same reference voltage for all layers, optimized for the entire block. But it's much better to use this one because each layer has actually a different threshold voltage distribution. So you actually want to have a different read reference voltage optimized for each layer. And you get better performance in terms of reliability if you do that. Okay, so there's modeling. Okay, we already said this. I already said this also. You adjust the read reference voltage for each layer, and you basically learn a voltage offset for each layer. That's the idea over here. And you can, again, read it in more detail, but you learn it once for each chip and store in a table, that offset. And you can predict the layer agnostic VOPT using existing models that we've discussed earlier. And this actually, if you actually do this layer to layer aware reading, you get rid of a lot of row bit errors. So it has a big effect, as expected, because there's a huge variation, right, between different layers in terms of error rate. Okay, so this is another idea over here. Again, I'm going to go through these very quickly. We don't have time to cover rate, but essentially, you have worst case row bit error rate that's much higher than average row bit error rate because of the layer to layer process variation. We want to significantly reduce worst case row bit error rate. And the key idea over here is you want to group flash pages on less reliable layers with pages on more reliable layers. So what is the idea of grouping? Grouping is if you actually group multiple pages together, if you get an error, you can actually reconstruct what the page looks like based on the grouping that you did. Let's assume that you have, I don't know, 5 pages grouped together. You store those 5 pages and the XOR of all of those pages, right, in some other location. If one of those pages fail, you can construct that page using the remaining pages plus the XOR of the pages. XOR is just one function that enables reversibility, right? That's the idea. By adding some redundancy, we store one more page that's encoded based on all of these other pages. And if you lose one of them, you could reconstruct that using that encoding. And a lot of RAID mechanisms work this way. It's called redundant array of inexpensive disks. Basically, it's developed for disks initially. You can store a page on multiple disks, and actually multiple pages on multiple disks, and actually have some redundancy. And that redundancy enables you to reconstruct some of the pages if you lose one of them. Well, it enables you to reconstruct n number of pages if you lose m number of them in the most general form, right? I gave you an example. When you actually cannot read one of them correctly, you can reconstruct it from 5 of them, 4 of the other ones. So this works nicely if your error distribution actually minimizes your worst case row bit error rate. So let's take a look at the grouping that you potentially do. So these are different chips, and these are different pages, and these are different word lines. Word lines are on different layers, and different layers have different characteristics. So if you actually group pages of the same layer, together in the same RAID group, this may have a very high row bit error rate. So all of them actually may fail at the same time, right? So if this one fails, this one also may fail, this one also may fail, this one also may fail. So if you group them together and XORed them or did something to them, added some redundancy, the probability that you're going to correct this is going to be much lower because all of them have very high failure rates, error rates. So the idea over here is to do the grouping. Well, I guess I picked that one because, so worst case arbor in any layer limits the lifetime of conventional RAID mechanism. I call it RAID, but it's actually applicable to any kind of error correction mechanism. If you group these things together and apply an error correcting code on top of that, if you have lots of errors as a result of your grouping, then the probability that your error correcting code is going to be successful is going to be low, right? So you really want to group things where you will have less number of errors. And that's the idea over here. You form your groups this way. Make sense? What does this do? This basically distributes the highest number of, the word line that has the highest number of errors across different groups. And this enables you to hopefully maximize the probability that you will be able to correct an error if you get one failure, if you get some number of errors. So that's the idea over here. So when you're actually reading this group, if you get an error, you can reconstruct it using these groups. That's the idea. Now, the one problem is, of course, you need to read different word lines now, right? If you get an error. You get an error in this particular page that you're reading. You need to read these three to reconstruct what this looks like. As a result, you need to do 1, 2, 3 reads. Whereas here, it was much nicer. You get an error over here. You already have read probably all of this. Or you can read it, depending on how your data layout is. Okay, so there's a downside to it. But the upside is you can actually get significant error reduction. And you can read the paper for the blanks. So you lose some space in this case. But that may be okay. Okay, so this gives you the space loss is about relatively small. And you can reduce the worst case row bit error rate significantly in this case, because you actually distribute this worst case across these RAID groups. Does that make sense? Okay, cool. So this is one last thing. Basically, we said that threshold voltage shifts quickly after programming. That's early retention loss. And we want to adjust read reference voltages based on retention loss. And that's essentially what we do over here. You learn and use a retention loss model online. And this is similar to what we've discussed earlier with data retention aware reading. And we try to predict, again, the VOPT using the model. So the benefit is, again, significant, because retention is a very big problem in 3D NAND flash. You get significant reduction on row bit error rate in this case. And as a result, you improve the lifetime quite a bit. So let's take a look at this example again. This is the worst case row bit error rate that limits your error correction. What lifetime your error correction capability buys for you. And this is the baseline, and that's the state-of-the-art mechanisms, if you use a lot of the mechanisms that we applied for NAND flash. And if you actually use layer variation aware reading, you get to the state-of-the-art by itself without using all those techniques. And if you actually add this layer independent RAID, you do this. And if you actually use all of the techniques that are developed in the paper, the curve looks like this. That's the row bit error rate. As a result, you get significantly longer lifetime. This should actually stop over here, but it's 85% longer lifetime for the given error correction capability. So if you actually don't want to change your lifetime compared to this blue baseline over here, you can reduce your ECC storage overhead significantly, as you can see. Because now your if you want to remain at this lifetime, PE cycle count, then you need a much weaker ECC, which has much less storage cost, much less complexity. Okay. Okay, I think I've discussed everything over here. I'm not going to go through this in detail. There's also some more things here, which basically adapts neighbor-assisted correction to the retention interference. Basically, there's retention interference caused by neighbor cells, and that's a big issue in 3D flash memory. you can change your neighbor-assisted correction mechanisms to take that into account. And you can imagine how you take that into account a little bit. Okay, so this conclusion I'm going to skip because we already covered all of that. But this is an example of 3D NAND flash being different from planar flash. It's a little bit more complex, as you can see, because now the layers add more complexity, and understanding them is actually not that easy. And going forward, I think it's not just going to be the layers, but everything else. As cells become smaller, layers become more, we're going to see more effects. So this is, the flash scaling problem will not get easy going into the future, because we don't have a fourth dimension to scale to, as far as I know, at least physically. Or maybe some of you know how to scale to the fourth dimension. Okay. Okay, and if you're interested, you can read this paper. That's the state of the art, basically, in 3D NAND flash memory, along with the other paper that I mentioned. Okay, how are we doing on time? Good? 2:14. Any questions? You guys have been silent today. Either these are really fascinating and you're just fascinated on looking at it, or these are really boring. Which one? Take a vote. Who's fascinated by this? Okay, some people, maybe. Yes. Yeah, good. Yeah, let's go back. That 21x plot. Uh-huh. Uh-huh. Yeah. Yeah, so that's, yeah, it's not perfect. Basically, the manufacturing is not perfect, and there are heat issues also that we don't fully understand or model. So my feeling is, yeah, the higher layers, as you see, well, the bottom layers, have somehow more heat, because you cool from the top, right? The bottom layer actually doesn't get cooled as much. As a result, I think there are heat effects that, in addition to interference effects, there are heat effects. And I think heat effects actually may be also maximum in the middle, right? Because things may get trapped. But modeling that, as far as I know, there are no good models for that. But that's a very good question, I think. Why is it not symmetric? What else? Yeah, there's a lot to discuss for every figure over here, actually. And we don't know enough because this is new technology. There's more that needs to be done. And we don't even know enough about DRAM, right? Of how heat gets distributed across DRAM. That's... What else? Any other questions? So the paper has some more discussion, so if you're interested, take a look at it. Let me go and skip these very quickly because this is going to be too fast, too slow with animation. No. Okay, I think this is much better. Okay, let's do this. So if there are no questions, I'm going to move to the next thing. Okay, I'll give you one more idea before we are done with flash memory lectures. This is going to be similar to what we've discussed earlier. I alluded to it. Actually, I gave the idea also. And this is basically the idea of grouping different blocks in different ways to fix the refresh problem. Yeah, I mean, we've discussed the refresh is employed. Unfortunately, actually, refresh is not good. When you actually are toward the end of the lifetime, if you're really pushing the boundary, frequent refresh consumes the majority of the endurance improvement. Meaning, you have some endurance improvement that you get from refresh, but if you're actually toward the end of your lifetime, you need to do a lot of refresh, and a lot of refresh causes a lot of remapping of the pages, of the same page. And that actually gets rid of some of your endurance improvement, because when you remap, you're actually doing program and erase cycles. Right? So you actually put in refresh to improve your program and erase cycles, but you're taking away from some of your program and erase cycles because of refresh. So these work against each other. Well, refresh enables some program and erase cycles, but it also takes away. So how do we actually reduce the refresh overhead? Reducing the refresh overhead becomes important here also, especially if you are toward the end of your lifetime in flash memory. And lifetime is going to be even more important going into the future, especially as we improve the capacities. So basically, there are a bunch of observations that you can make. You can apply techniques like RAIDER, like we discussed, retention-aware intelligent DRAM refresh, in flash also. But one of the examples is to take advantage of the access pattern. It turns out refresh is unnecessary for write-hot data. The basic idea over here in this work is to physically partition write-hot pages and write-cold pages within the flash drive to different blocks, and then apply different policies to the block. So if a block is write-hot, you basically don't refresh that block as often. Maybe you don't refresh it at all, right? I don't know. And you could actually apply different policies. As we discussed again in the earlier flash lecture, I remember I drew this picture on the board where you partition your drive into different types of blocks, and you can apply now different policies. You can apply different wear leveling policy, different garbage collection policy, because you have different write behavior. If some pages are not being written a lot, then you don't need to collect that garbage as much, right? Okay, so it turns out if you do something like this, you improve lifetime significantly, and even if you do adaptive refresh on top of that. You basically get significant lifetime improvements if you take a system that is already doing refresh and put this on top of that. Okay, basically the key idea is, okay, I'm going to skip this. This basically shows that you can read, write on a page granularity, but you erase on a block granularity. In existing systems, you can do refresh on a block or page granularity, but this paper makes a case for doing this on a block granularity. Today, what you do is you basically allocate pages this way. You may have hot pages, cold pages that are mixed together. And as a result, if you want to refresh the block granularity, you have to refresh everything, right? But if you actually do this, separate hot and cold pages with some prediction mechanism, then the key question is how do you predict what's hot and what's cold? Then read the paper. Now you can actually do different things. Basically, you have these write-hot blocks and other write-hot blocks and write-cold blocks. And you can relax the retention time for the write-hot blocks. Again, this is a general concept. The idea is basically to separate blocks or pages with different separate pages with different access patterns to separate parts of the drive. Access pattern may be based on write hotness. How often do you write to this block? It could be based on read hotness also, right? How often do you read this block, right? If maybe you want to put the blocks that you read a lot together, read hot versus read cold, right? If you do it together, then that leads to some potential benefits, but also that could lead to downsides. Right now you do a lot of read disturb on those blocks, right? So the key question is how do you balance these things? I'm not going to go into the detail, but there's a lot that goes on in a flash drive that looks like this today. And if you want to get a glimpse of it, this is the work that introduced the idea of write hot, write cold partitioning and saving the refresh based on that. So now we're almost at the end of flash memory. Okay, I'm not going to cover some of these works, as I said. You can read the vulnerabilities work over here. And if you really want to get the entire summary, this is the paper to read. And actually, maybe I will assign this. It's a bit longer than the paper that you read, but this is work that we've actually written this paper for a year, more than a year or so. I was actually writing this last, wait a second, when was this published? 2017, now I remember. So we're in 2018 this year, right? Good. During the Christmas and New Year's, we actually did a lot of progress in writing of this paper last year. Wait a second, that doesn't make sense. That must have been the previous year. Okay. It's amazing how years pass by. Okay, so yeah, this was fun. Okay, and that's the end of the lecture for flash memory. And I think I'd like to take questions right now, because I'm not sure if I want to start the next topic today. Any questions? We've covered a lot so far. You can ask questions about anything that we've covered. Flash memory is certainly fascinating. As I said, this is going to be even more important when emerging technologies emerge. And some of them are really almost emerged, like the 3DX point, right? And there are already SSDs, but there's going to be memory 3DX point soon. And understanding those technologies and making use of them will be important. DRAM is important, as we know. Yes, one question. That's a great question. My feeling is yes, some of them, certainly. Some of them are not applicable because the device doesn't operate that way. But some of them, I believe, have yes. But there's not enough public information in that area, unfortunately. Yeah. For example, I'll give you an example that's more or less public. Basically, wear leveling. These emerging technologies have an endurance problem similar to flash. So they all need to do wear leveling internally. And some of the techniques that have been inspired by flash are used for PCM SSDs, for example. But of course, they're a little bit more efficient and slightly different. But refresh is another example. PCM as a retention loss phenomenon. There's some amount of refresh that goes on in those devices also. But there's more to come, especially as these devices become analyzed. We'll understand them more. And yes.
So could it be like that one-to-one mapping that we have in DRAM, like address also gets like more broken up if you use PCM? In additional hard disk, you have like block sectors like there, and the SSD like moves around.
Exactly, yeah. So in PCM, it could move around also, yes. It's very hard to tell without public information. But with the endurance problem, you have a layer of remapping potentially. Right? It does move around with wear leveling. But the mechanisms, maybe in Flash, for example, you have this mapping table, right? The DRAM is used as a mapping table. You get as I discussed last time, you have a logical address coming in, and then you have a physical Flash address that's translated. That kind of access may be too high overhead for PCM. Because in Flash, your access latency is very long anyway. What is another DRAM access before that? But in PCM, your access latency is closer to DRAM if you want to do another DRAM access before it.
Because if I remember correctly, like the architecture for PCM, you assume somewhat of real living.
That's right, exactly, yeah. Exactly, yes. In that work, actually, we assumed there's wear leveling, perfect wear leveling. Even then, you didn't have good lifetime, right? Yeah. Yeah, so there is some wear leveling that is employed, and people have proposed it. I'd be happy to point you to some of them if you're interested. Yeah, so the low latency is usually achieved by arithmetically determining the address you map to. So once in a while, you shift the mapping that you have. Of course, this requires moving some blocks, but if you do it infrequently enough. In Flash controllers, it's very heavyweight because you basically have full flexibility as to where you map an address, right? That requires a full mapping table. But if you actually take an arithmetic function of the address and you shift that function to point to different locations once in a while, then you actually do the wear leveling more efficiently. It's called start gap wear leveling. It was published in Micro in 2009. That's one example of a more efficient wear leveling technique. Yeah. These are very good questions. What else? More questions? Comments? Ideas? Oh, hard disk lecture. You would like that? Or that's the natural progression, you think? No, I don't think that's going to happen anytime soon. I mean, those things are also fascinating, but It's good to know how things operate, for sure. You mean in the remaining part of the course? We'll talk about multi-core, but we're not going to look into the hypervisor a lot. That's a bit. It should be covered in a more operating system course, but maybe in a future incarnation, yes. There are a lot of interesting things over there also, like scheduling and resource management. We're going to touch into resource management issues, but not as much from the hypervisor. Yeah, unfortunately, we don't have much time. And there are a lot of fascinating things. I find hard disk very fascinating, for example. Yeah, the problem is there should really be a storage systems class probably to teach it. I'm not sure if it exists. Probably not. But also, I think it's good to know, but the technology itself is not going to flash memory is actually a revolutionary technology, I think. That's really displacing a lot of the hard disks quite a bit. Like even in terms of reliability, flash memory is much better. People didn't think that would be the case, but compared to moving parts, mechanical parts, error rates that are seen in the field shows that flash memory is a better option. But of course, cost-wise, hard disks are hard to beat compared to flash memory. And then the next lecture could be on tape. I'm not sure if anybody teaches that actually at this point. Yeah, definitely. There are multiple. We've developed one which was published in FAST last year. But there's more to do, I think, especially integrating that simulator with DRAM simulation is going to be very important, I think. And you could adapt that simulator to simulate emerging technologies also, like phase change memory. I think that's a very good direction to study these effects. Yeah, absolutely. Protocol is always your limiter. So right now, a lot of the flash devices don't use SATA. It's more PCIe, a faster, higher bandwidth protocol. But you can still find devices that use SATA, I think. But you're limited, basically. You're limited as to what you can express, and you're limited as to what you can send back, right? It'd be much nicer if the whole system was integrated much closer to each other. That's right, yes. You're limited by the bandwidth over there. Device actually can be much more capable, potentially, in terms of latency, especially latency. But you have to go through this interface. That's very limited. And also, you cannot express much from that interface, right? If you're running an application has some characteristics. Today, actually, people want to do that, but they're limited by that interface. For example, I want to say, okay, I access these pages very, very frequently. If I want to communicate that to the device, there's no way. It's all discovered today by the device somehow. Yeah, but that's a great question, I think. Those interfaces are some of the most limiting things that we have in systems today. The DRAM interface, the SSD interface. Yeah, you might want to try attaching a flash chip directly to your processor without the interface. But you need some sort of interface, of course. But if you do that, then you get rid of a lot of that overhead that you have in the protocol. Yeah, there are three big limiters to innovation, I think, in research, or maybe in general. One is mindset. If you don't have the right mindset, you limit your innovation to begin with. The second is interfaces. If you don't have the right interfaces, you limit the innovation because you partition things in the wrong way. I think the third one is reviewers. They limit innovation also by being unreasonable. If you want to generalize that, I guess people who are against innovation are that's also about mindset, but mindset goes across, right? It's the researcher's mindset as well as the people's mindset. But interface is a big, in my opinion, interfaces are up there. It's a very hairy place because it's very hard to change some of these interfaces because there are a lot of players involved in it. Yeah, if you have an evolving interface that's much more open, that could be a good way. Okay, any other questions? This is a good discussion. We should have more of that, I think.